Hello and welcome to this revision session for AQA A-Level Physics, Paper 1 on the topic of particles, in particular particle physics and quantum physics. So if we've been successful and we've learned in today's revision session, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? Well, when you're completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section, write down your working out and answers to the question in the revision session. When you're doing this, make sure you write in full sentences and show the full working out. Whilst in the right hand side, write down any bits of information which you find useful or any hints and tips on answering questions from this revision session. At the end of the revision session, write up these notes into a revision sheet for you to use independently. Now, how should you be revising A-Level Physics? Well, the first thing to do is to learn the key facts. Use the revision guides, the class workbooks, the student prep notes and the textbook to learn the key ideas of the course. You may wish to make mind maps or to write out notes yourself. The second step is to test yourself. Use things like Caboodle, Seneca, student knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. Finally, you should practice examination questions, so use exam prep books, homework books, study books and additional workbooks to answer exam questions and mark your own work. Now, you may wish to download your own exam past papers to do this. So the three steps of learn the key facts, testing yourself and practicing exam style questions are how you should be carrying out revision. Now, in this revision session, we're going to be focusing on two types of questions today. The general check questions, which are basic questions designed to probe your understanding of the key concepts of the topic. And then secondly, assessment point questions, past paper exam questions, which will mimic the types of questions found in public examinations. So let's start off with our key checks on particles. So to assess your understanding, quickly answer the following. Calculate the energy of a photon of frequency 4 times 10 to the 18 Hz. So pause the video now, then unpause the video when you want to go through your answer. Right, E equals HF, which we know to be 6.63 times 10 to the minus 34, times by 4 times 10 to the 18 is 2.7 times 10 to the minus 15 joules. The next question says, in a microwave oven, photons of energy 1.02 times 10 to the minus 5 eV are used to heat food. Express 1.02 times 10 to the minus 5 eV in joules. So pause the video now, then unpause the video when you want to go through your answer. Right, the answer to convert from EV into joules is to multiply by 1.6 times 10 to the minus 19. So our answer becomes 1.63 times 10 to the minus 24 joules. The next question says, calculate the frequency of these photons. So pause the video now, then unpause the video when you want to go through your answer. Right, for this question we're going to be rearranging the previous equation we used. So F is equal to E over H. So we know our energy in joules, we know our value for Planck's constant, so we work it through to be 2.46 times 10 to the 9 Hz. The next question says calculate the wavelength of these photons. So pause the video now, then unpause the video when you want to go through your answer. Right, again we know lambda is equal to the speed of light over frequency, so we can pop in all the values and we get 0.12 meters. The next question says list all of the positive quarks available. So pause the video now, then unpause the video when you want to go through your answer. Well, this is a knowledge-based question and our positive quarks are the up quark, the charmed quark and the top quark. Next question, state the quark combinations for the proton and the neutron. So pause the video now, then unpause the video when you want to go through your answer. Right, again this is just knowledge. Protons are up, up, down, the neutron is down, up, down. The next question says compare baryons and mesons. So pause the video now, and then unpause the video when you want to go through your answer. Right, baryons and mesons are both hadrons, so they both mediate the strong interaction and are made from quarks. Baryons have 3 quarks and mesons have 1 quark, 1 antiquark. The next question says, what is the antiquark combination of the antineutron? So pause the video now, then unpause the video when you want to go through your answer. Well, the antiquark combination is always just going to be the antiquarks of the normal in comparison to the quarks of the normal particle. So the antineutron is anti-down, anti-up, anti-down. The next question says, figure 30.18 shows another energy level diagram. In this case, energies are given in electron volts. From the list below, state which photon energies could be absorbed by such an atom. 6 eV, 9 eV, 11 eV, 20 eV, 25 eV, 34 eV, and 45 eV. So pause the video now, then unpause the video when you want to go through your answer. So 9 eV, 11 eV, 25 eV, 34 eV, 20 eV and 45 eV all correspond to differences between energy levels, so will all be absorbed by the atom. 6 eV does not correspond to any difference in the energy levels, so cannot be absorbed. A student claims the strong nuclear force pulls all protons and neutrons together at any distance, and it gets stronger the closer they are. Evaluate this statement and explain what is correct and what is incorrect about it. Include the range of the force in your answer. So pause the video now, then unpause the video when you want to go through your answer. Well, the correct part of this statement is that the strong nuclear force is responsible for holding the nucleons together in the nucleus. It is a short-range attractive force and is essential for overcoming the electrostatic repulsion between the positively charged protons in the nucleus. But the incorrect part is that the strong nuclear force only acts significantly over distances up to 3 femtometers. At separations less than 0.5 femtometers, the force becomes strongly repulsive, preventing nucleons from collapsing into each other. Therefore, it doesn't get stronger the closer they are, it switches from attraction to repulsion at short range. The next question says, a nucleus of uranium-238 undergoes alpha decay. A student writes the following equation and says it's correct because the mass numbers add up. Evaluate this statement. So pause the video now, then unpause the video when you want to go through your answer. So the student has included an electron, a beta particle in the alpha decay. That's incorrect. Alpha decay involves the emission of a helium nucleus only. There are no electrons, so therefore electrons are only emitted in a beta minus decay, not an alpha decay. The next question. A student says in beta minus decay an electron is emitted and the total energy of the decay is just shared between the new nucleus and the electron. Explain why the statement violates a conservation law. So pause the video now, then unpause the video when you want to go through your answer. Now, if only the electron and the nucleus shared energy, then all beta particles should have the same energy. In addition, the lepton number is not conserved in this decay either. Now, experiments have shown that beta particles have a range of energies, meaning that energy is missing if only the electron and the nucleus are considered. So to conserve energy and momentum, another particle must carry away the missing energy, the antineutrino. A student says that the electromagnetic force and the strong nuclear force are both infinite in range and the weak nuclear force is stronger than the electromagnetic force. Evaluate the statement. Which parts are correct or incorrect? So pause the video now, then unpause the video when you want to go through your answer. Now, the electromagnetic force is long range, it's infinite as it's mediated by a massless virtual photon. The strong nuclear force is short range, acting only up to about 3 femtometers. It is not infinite. Now, the weak interaction is weaker than both the electromagnetic force and the strong force and has a very short range, about 10 to the minus 18 meters, due to having a very massive exchange particle, the W boson. A student claims that exchange particles are real particles that travel between interacting particles at the speed of light, carried energy with them like a thrown ball. Evaluate the statement and clarify the role of virtual exchange particles in fundamental interactions. So pause the video now, then unpause the video when you want to go through your answer. Now, exchange particles in force interactions are typically virtual particles, not directly observable. They exist only during the interaction and cannot be detected independently. So in quantum field theory, virtual particles are not like classic projectiles like balls. They mediate momentum and energy transfer between particles, but they don't follow classical motion, and they can actually violate conservation laws for the moment that they exist. A student draws a Feynman diagram for beta minus decay and claims it shows the weak interaction correctly. The neutron goes to the proton and electron. Identify the two key emissions in the student's representation. So pause the video now, then unpause the video when you want to go through your answer. Well, firstly, the W minus boson is missing. That's the exchange particle needed to mediate this weak interaction. And the antineutrino is also missing. To conserve energy, momentum, and lepton number in beta minus decay, you will also need an antineutrino. The next question says, a student states in beta minus decay a proton changes into a neutron, and in beta plus decay a neutron changes into a proton. Identify the error in the student statement. So pause the video now, then unpause the video and you want to go through your answer. Well, the truth is, in beta minus decay, a neutron turns into a proton, not the other way around, and in beta plus decay, a proton turns into a neutron. A student suggests that the following interaction is possible. A proton plus an electron goes to a neutron, a neutrino, and a pi zero. Using conservation laws, assess whether this reaction is possible. So pause the video now, then unpause the video when you want to go through your answer. Now this is possible because everything is conserved. Because if we look here, we know that the charge beforehand is plus 1 minus 1, which is 0. Afterwards it's 0 plus 0 plus 0, 0 before, 0 after. Baryon. So beforehand it's plus 1 and 0, so that equals 1. On the right hand side it's plus 1, 0 and 0, so therefore it's 1 afterwards, so it's conserved. In terms of lepton number, it's 0 and plus 1 before, so that equals 1, and afterwards it's 0 plus 1 and plus 0 again, so it's 1 afterwards, so it is conserved. Beforehand the strangeness is 0, and afterwards the strangeness is 0, so therefore all our different factors are conserved. The next question says, a student says, in all interactions strangeness must be conserved. Is this statement always true? So pause the video now, then unpause the video when you want to go through your answer. Now this statement is not always true. Strangeness is conserved in strong interactions and electromagnetic interactions, but in weak interactions strangeness can change by either plus 1 or minus 1. A student says any light, no matter how low the frequency, will eventually cause electrons to be emitted from a metal if the light is intense enough. Identify the misconception in this statement. So pause the video now, then unpause the video when you want to go through your answer. Right, the student assumes that increasing the intensity or brightness of light can cause electrons to be emitted even if the frequency is too low. That is not the case. The only factor that can affect if electrons are emitted from a metal is the frequency of the photon. The next question says, explain what is meant by threshold frequency and why intensity alone is not enough. So pause the video now, then unpause the video when you want to go through your answer. So, the threshold frequency is the minimum frequency required for photons to have enough energy to overcome the work function of the metal. We know h times by f0 is equal to the work function. So if the f0 is greater than f, no photon electrons will be emitted regardless of the intensity. Intensity increases the number of photons that would hit the metal, not the energy of each photon. Only photons with a frequency greater than the threshold frequency can release electrons from the metal. A student says the stopping potential is how much energy the light must have to start photoemission. Explain why the statement is incorrect. So pause the video now and unpause the video when you want to go through your answer. Well, the student confuses the idea of stopping potential with threshold energy. The stopping potential is not the minimum light energy required for photoemission. That is going to be the potential required to bring the photoelectrons emitted to a stop after they've been emitted from the metal. A student says excitation and ionization are the same thing. Both just mean the atom absorbs energy. Once again, identify the misconception in this statement. Now the student here is failing to understand that although both involve energy absorption, they result in very different outcomes for the atom. The next question says, clearly distinguish between excitation and ionization. So pause the video now, then unpause the video when you want to go through your answer. Well, in excitation, an electron absorbs energy and moves to a higher energy level. The atom remains neutral, and the electron then returns to a lower level later, emitting a photon. In ionization, an electron absorbs enough energy to be completely removed from the atom. This leaves behind an atom which is a positively charged ion, so the atom is no longer neutral. The next question says, in a fluorescent tube, the free electrons collide with mercury atoms. What process occurs in the mercury atom during this collision? So pause the video now, then unpause the video when you want to go through your answer. Now in this collision, the free electrons collide with bound electrons in the mercury atom. If they transfer the right amount of energy, the bound electrons in the atoms are excited to higher energy levels. Now, what does the appearance of distinct lines in the hydrogen spectrum tell us about energy levels? So pause the video now, then unpause the video when you want to go through your answer. Well, the line spectrum of hydrogen contains discrete lines, not a continuous spread of colours. Each line corresponds to a photon of specific energy emitted when an electron transitions between two fixed levels. Now, since only certain energy level differences are allowed, only certain frequencies or wavelengths of light are emitted. This again provides strong evidence that electrons in atoms occupy discrete energy levels and that the energy is in fact quantized from the photons. So let's now have a look at some exam-style questions on this topic of particles. So to assess your understanding and answer the following, physicists analyse data from a bubble chamber where a short-lived particle, X, is observed to decay into three products, a kaon, a pion and an antineutron. They are confident that the particle X does not contain any charm or bottom quarks. They also confirm that the total charge before and after the decay is zero and that the baryon number is conserved in the process. Use the information provided, deduce the possible quark structure of particle X, justify your reasoning by considering the quantum numbers of the decay products, and then explain why the decay of X provides evidence that the strange quark is involved in this interaction and state what this suggests about the type of interaction responsible. So pause the video now, then unpause the video when you want to go through your answer. So in this first one, we know that the antineutron is going to be anti-up, anti-down, anti-down. So it has a baryon number of -1 and a charge of 0. Now our kaon could either be K plus or could be K0, or they're antiparticles. Now this idea for the pion, it could either be a pi plus, a pi minus, or a pi 0, and it gives that particular quark structure. Now we know the total charge after the decay must be 0 because we know that beforehand it was also going to be 0, so it must be add up to 0. So we know that beforehand there must be actually a combination that gives us a 0 charge. So it could be K0 plus pi 0 plus the antineutron, or it could be K plus pi minus plus the antineutron. Now the total baryon number afterwards is -1, so therefore X must have a baryon number of -1. So that tells us straight away that X must be an antibaryon. So there's two possible outcomes for this. It could either be an antiproton, which is anti-up, anti-down, or it could be something which is an antibaryon, which has a strange quark in it, or strange antiquark in it, like sigma minus. Now the next question, we know that a kaon must by definition contain a strange quark or antiquark, so the strange quark must be present in X or created in the decay. Now strangeness is not conserved in the decay. The kaon has a strangeness of plus or -1 and the others have a strangeness of 0. So this implies that the decay must occur via the weak interaction, as strangeness is conserved in the strong interaction but not in the weak interaction. The next question says, engineers servicing a PET scanner observe a brief but intense radiation spike in the detector. They suspect a malfunction caused a burst of positrons to be released into the detector housing, where they rapidly interact with electrons in the surrounding metal. The detector system registered two simultaneous high-energy photons moving in opposite directions. The team wants to calculate the energy of each photon and confirm that this event aligns with known theoretical expectations. Explain what happened in the detector during the event. Include the names and properties of the particles involved and the process by which the photons were produced. Using known rest energies, estimate the energy of one of the photons produced in this process. And then the PET scanner operates using photon detectors sensitive to wavelengths down to 3 × 10 to the -12 meters. Discuss whether the photons observed in this effect will be detectable by the system. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, a positron encountered an electron, leading to the process of annihilation. Annihilation results in the conversion of a particle and antiparticle mass into energy. Two gamma photons are always going to be produced, emitted in opposite directions to conserve momentum. Now the positron and electron have an equal mass and opposite charge, each with a rest energy of 0.511 MeV. Now this tells us that the total energy from annihilation must be 0.511 MeV plus another 0.511 MeV from the other particle. So therefore it's 1.022 MeV. Now the two photons produced will share this energy equally. So it's 1.022 divided by 2. So each photon has an energy of 0.511 MeV. Now, if you use E equals hc over lambda, we know lambda equals hc over E. Pop in all of our values. Remember to turn our energy from mega electron volts into joules. So we get our answer to be 2.43 times 10 to the minus 12 meters. Now, this wavelength is in fact shorter than the minimum value can be measured, which is 3 times 10 to the minus 12. So therefore, the photon would not be detectable by the PET scanner system. The next question says, in a collaborative experiment between international research labs, scientists observed the decay of an unknown charged particle X in a bubble chamber. The decay of X leaves a curved track, producing 3 visible particles labelled A, B and C. A separate detector later identifies A as a positively charged pion, B as a neutral kaon, and C as a muon. The curvature of X's track suggests that it had a greater mass than any of the products. The data also show the total lepton number before and after the decay is conserved. Strangeness is not conserved in the process. So identify the interaction responsible for the decay of particle X. Justify your answer with conservation laws and the nature of the particles involved. The kaon is known to carry strangeness. Use this information to infer what the strangeness of particle X might have been and explain what the lack of strangeness conservation tells you about the decay process. Then, using the identities of A, B and C, determine whether particle X could have been a baryon or a meson. State your reasoning based on baryon number, lepton number and quark content. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that the decay is producing a muon, which is a lepton, so a lepton number must be involved. Now, strangeness is not conserved in this decay, so it can't be a strong interaction. So therefore, the decay has to be due to the weak interaction. Now, the weak interaction allows changes in strangeness and also includes leptons in the decays as well. Now in this next one, we know a neutral kaon has a strangeness of +1. Now since strangeness is not conserved, particle X must have a different strangeness. So this reinforces the idea that the decay occurred via the weak interaction, which allows the strangeness to change by plus or minus 1. Now in the last part, the pion and the kaon are mesons, the quark-antiquarks. So the muon is a lepton, and therefore no baryons. So the baryon number before and afterwards must be 0. So X cannot be a baryon. Now the total lepton number after includes 1 lepton, a muon. So therefore, another muon neutrino must be emitted but not be visible in the detector to maintain lepton number conservation. So therefore, particle X must actually probably be a meson with a 0 baryon number, a 0 lepton number, and be massive enough to decay into the observed products. The next question says that physicists studying unstable isotopes of an artificially produced element, zendonium, observed 2 different decay processes. In one isotope, a neutron decays into a proton. In another, a proton-rich isotope decays into a neutron. The researchers summarized observations in the table. Describe the quark level change that occurs in each of the 2 beta decay processes, include the identity of the affected quark and how this leads to the observed change in the nucleon. And then for each decay, demonstrate that charge, baryon number and lepton number are conserved. Then a student claims that the beta decay emits a lepton, energy must not be conserved in this interaction. Evaluate this claim using the principles of conservation and the reason based on the nature of the beta decay. So pause the video now, then unpause the video when you want to go through your answer. Well, in this first one, in the beta minus decay, a down quark changes to an up quark, transforming a neutron into a proton. In beta plus decay, an up quark changes to a down quark, transforming a proton into a neutron. Now these processes must involve the weak interaction because there's leptons present and it changes the quark flavour. So the change in quark type accounts for the nucleon transition we observe in each decay. Now in the next one, for the beta minus decay, the charge is 0 before and then afterwards is +1, -1 and 0, so 0 afterwards. The baryon number before is 1, then afterwards it's 1, so therefore that is conserved. And then the lepton number is 0 before and then it goes to +1 after, -1 after, which is 0, so it's conserved. Now finally, we can look through it all, and for the beta plus decay, we can say the charge before is +1, afterwards is 0, +1 and 0, so the total is +1. The baryon number before is 1 and afterwards is 1. The lepton number is 0. It then goes to -1 and +1 to 0. So therefore it's all conserved again. So this tells us that for the beta minus decay, the lepton number must be 0. Therefore it works it through, so we can see it is 0 and it's the same for the other process. So there's where those different marks come from. Then the final part, the student misunderstands the conservation of energy. Energy is conserved in the beta decay. The presence of a lepton does not violate energy conservation, it shares the released energy with other decay products. Now the decay products have a kinetic energy, so the total energy of both the mass and the kinetic equals the original mass energy of the unstable nucleus. So the energy is being redistributed but not lost. The student's claim is incorrect. The next question says, an industrial lighting engineer is assessing the performance of a fluorescent tube in cold storage warehouses. The lamp contains mercury vapor and relies on electron collisions to excite mercury atoms. The resultant UV photons are absorbed by a phosphor coating, which then emits visible light. The engineer collects the following data during a test. Now the manufacturer claims that the ideal operating energy is 6 eV, but the engineer notes reduced efficiency at higher electron energies. So explain the process of excitation and ionization in the context of fluorescent tubes and identify what data points correspond to each process. Then, using the data provided, estimate the energy required to excite a mercury atom to its first visible emitting state and state your answer in joules. Then evaluate the manufacturer's claim that 6 eV is the ideal operating energy. In your answer, consider the atomic processes involved, the energy conversion efficiency, and how electron energy influences light output. So pause the video now, then unpause the video when you want to go through your answer. Right, so in the first one, excitation occurs when an electron transfers energy to an atom, raising an internal electron to a higher energy level without it being ionized. Now, ionization occurs when an incoming electron transfers enough energy to completely remove an atomic electron. So at 4.9 eV, that's our first status for excitation, and it's consistent because you get a visible faint glow. Now at 10.2 eV, the additional energy leads to higher excitation states and possibly even UV emission. Now at 15 eV, we've likely now surpassed the ionization energy of mercury, so there are now fewer useful transitions and it's now a decreased efficiency. Now in 1.2, the first significant visible glow you get is at 4.9 eV, so that must be an excitation energy. So to then work it out into joules, we multiply by 1.6 times 10 to the minus 19, so it's 7.84 times 10 to the minus 19 joules. Now we know that 6 eV gives strong emission, and this matches the known efficient excitation transitions in mercury. Now at this energy, electrons are more likely to excite atoms without ionizing them, maximizing their light output. Now the higher energies may cause ionization or less efficient transitions, so you might get UV photons or energy lost as heat. Now ionization doesn't contribute to visible light, it may result in a loss of control over the energy states. Now too low energy, like 3.5 eV, fails to excite the mercury, so there's no emission at all. So 6 eV is a reasonable compromise. It's above the excitation threshold, but below the ionization threshold. So the manufacturer's claim is correct. The next question says, pions are created in the upper atmosphere where high energy cosmic rays interact with nuclei. Pions are mesons and they quickly decay to muons. Muons are leptons with a mass of 106 MeV over c squared. Give a possible quark structure of a pion. Now the equation shows the pion decaying into a muon and antineutrino. Energy and momentum must be conserved in this decay. Explain 2 other conservation laws that apply to this decay, and then calculate the mass in kilograms of a muon. So pause the video now, then unpause the video when you want to go through your answer. Right, so your pion must be a quark-antiquark and can't contain a strange or anti-strange because then become a kaon. So it's up and anti-down, up anti-up, down anti-up. You could also have anti-up and down as well. So the next one, What must be also conserved is charge. We know how before, and it's -1, and afterwards it's -1 and +0, so it's conserved. We must see lepton numbers conserved. It's 0 before, because it is going to be a meson. It's then +1, and then -1 afterwards, so therefore it's 0 before, 0 afterwards. And none of them are baryons, so the baryon number before is 0, and afterwards it's 0. Now, firstly, to work out your mass in kilograms, let's turn our energy into joules. So we go 106 MeV times by 1.6 times 10 to the minus 19 joules. So we get our energy to be 1.70 times 10 to the minus 11 joules. We know that the mass is equal to energy over c squared. Pop in those values and we get 1.88 times 10 to the minus 28 kilograms. The next question says, describe the interaction that's responsible for keeping protons and neutrons together in a stable nucleus. You should include details of the properties of the interactions in your answer. Nuclei can decay by alpha decay and by beta decay. In alpha decay, only one particle is emitted, but in beta decay, there are two emitted particles. Explain how baryon number is conserved in alpha and beta decay. Kaon decays by the weak interaction. The equation shows an example of kaon decay. K0 goes to pi plus pi minus. State one feature of this decay that shows us an example of the weak interaction. Then there have been considerable advances in our understanding of particle physics over the past 100 years. Explain why it's necessary for many teams of scientists and engineers to collaborate in order for these advances to be made. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, what's the fact about the strong interaction? So it has a short range, or up to a range of 5 femtometers. Its attraction up to this point. It's repulsive at any distance below 1 femtometer. It's negligible or 0 beyond 5 femtometers. It only affects things made from quarks, hadrons, baryons and mesons, and is mediated by the gluon or the pion virtual exchange particle. Now in alpha decay, we know that the baryon number will be conserved as the number of protons and neutrons is unchanged, because a proton is a baryon and a neutron is a baryon, and it's only having protons and neutrons being released from the nucleus in alpha decay, so therefore there's not going to be a change in those values. Now in beta decay, a neutron changes into a proton, but they've both got the same baryon number, so it's going to give the same value. Now a beta minus particle and an electron antineutrino are also produced, but they both have a 0 baryon number, so it won't affect the baryon number. Now, one feature of the weak interaction is that strangeness is not conserved. Now, why is it important to have a collaboration of many teams? Well, the results of experiments must be independently checked and validated or peer-reviewed before they're accepted. Particle accelerators are very expensive, and collaboration helps spread the cost of building them. There are many skills and disciplines required for particle physics, and there's lots of data to process. You need lots of teams to work on this data. The next question says, some students investigate the photoelectric effect. They use a piece of magnesium ribbon placed inside a cylinder of copper gauze as shown. There's an air gap between the copper gauze and the magnesium ribbon. The copper gauze was connected to the positive terminal of a power supply. The magnesium ribbon and a sensitive ammeter were connected to the negative terminal of the power supply as shown. The students made the following observations. When light from an ultraviolet lamp was incident on the gauze and ribbon, a current was detected by the ammeter. When the polarity of the power supply was reversed, the current decreased to 0. Explain these observations. So the student reconnected the circuit so that a current was detected when ultraviolet light was incident on the gauze and ribbon. The student replaced their original lamp with an ultraviolet lamp with a much greater intensity. Explain the effect that this had on the experiment. And the ultraviolet lamp was replaced by a laser which emitted red light of wavelength 633 nanometers. Deduce whether the photoelectric effect will occur. The work function of magnesium is 3.7 eV. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, photons of UV light will cause electrons to be emitted from the surface of the magnesium. Now the photon energy must therefore be greater than the work function of the magnesium, as the frequency of the UV light is greater than the threshold frequency of the magnesium. Now electrons are attracted to the positively charged gauze because it's a negative going to a positive, and this creates a current. Now when the polarity is reversed, the current is 0 because the electrons will no longer have enough kinetic energy to move across the gap and create a current. In our next question, the greater intensity increases the rate of photon emission from the lamp. This leads to an increased emission rate of photoelectrons, so you get a greater flow of charge leading to a greater current. Now the frequency of light is going to be c over lambda. So you pop those values in and you get 4.74 times 10 to the 14 Hertz. Now E equals HF for a photon. So you pop that through and you get 3.14 times 10 to the minus 19 joules. We know the work function, if we convert it from EV into joules, is going to be 5.92 times 10 to the minus 19 joules. So the energy of the photon is less than the work function. So therefore electrons cannot be liberated by the photons, so the photoelectric effect does not take place. The next question says the Planck constant is an important universal constant used in the study of the wave-particle duality. In a demonstration of the photoelectric effect, ultraviolet radiation with a frequency of 2.8 times 10 to the 16 Hz is incident on the surface of clean zinc. Electrons are released from the surface of zinc. Calculate the maximum velocity of the released electrons. The work function of zinc is 6.9 times 10 to the minus 19 joules. Atomic electrons are confined within the atom. One model of the atomic electrons suggests that in the wave associated with an atomic electron forms a standard wave that fits exactly into the diameter of the atom. The diagram shows the lowest frequency standard wave that can fit into the diameter of the atom. Calculate the momentum of the electron, where the diameter is 2 times 10 to the minus 10 meters. Now the electrons in an atom can only exist at discrete energy levels. Explain how the standard wave model can account for this. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that the kinetic energy is going to be equal to the work function, which is going to be HF, minus the kinetic energy of the it's going to be the energy of the photon, my apologies, HF, minus the work function. So we work that through and we get it to be 1.78712 times 10 to the minus 17 joules. We therefore know our kinetic energy is equal to that, and we know kinetic energy is a half mv squared. So therefore V is going to be equal to the square root of 2 times by this energy over the mass of the electron. Now we know the mass of the electron is given to us, it's 9.11 times 10 to the minus 31 kilograms. So our answer is 6.26 times 10 to the 6 meters per second. Next, we must use the de Broglie wavelength equation. So the de Broglie wavelength is equal to h over the momentum. So we get that out to be 6.63 times 10 to the minus 34 over 2 times by 2 times 10 to the minus 10. So therefore, we get 1.67 times 10 to the minus 24. Now the next question, how does it link in? Well, a discrete number of half wavelengths will fit into the diameter of an atom. So this therefore leads to the discrete energy levels that electrons can exist in the atom. The next question shows a picture which has the electron diffraction pattern produced by graphite in a cathode ray tube. So describe the experiment that produces this pattern. You can draw a labeled diagram of the apparatus to help you. Explain why the light and dark circles are shown in the picture produced, stating what this evidence provides about electron behavior. A potential difference of 5 kilovolts is used to accelerate the electrons. Calculate the work done on the electrons. Calculate the de Broglie wavelength of the accelerated electrons, and suggest a value for the spacing between the graphite atoms. Justify your answer. So pause the video now, then unpause the video when you want to go through your answer. So in this first question, in an evacuated tube, electrons are released by thermionic emission, and the emission of the electrons from the cathode or the filament gun or the electron gun then allows the electrons to be accelerated towards the anode, or the accelerated through the electric field. They're then diffracted through a graphite target as the graphite is thin, and at that point the electrons are detected on a screen, and the electrons will produce visible light on impact with the screen to allow us to see these rings. Now this provides evidence for the wave nature of electrons, because electrons are diffracting. It's a wave process. Now the light circles are caused by constructive interference taking place, where the waves arrive together in phase. The dark circles are caused by destructive interference, where the waves of the electrons are arriving in antiphase. We know in our next part that the work done is equal to the charge of the electron multiplied by the potential difference. That's an equation from electricity. So E equals QV. We know the charge of an electron, we've got the potential difference, so we get 8 times 10 to the minus 16 joules. We know that in this case the work done is as kinetic energy because the electrons are being liberated and then moving. So our work done is a half mv squared. So therefore we can work out V when we put in all the values to be 4.2 times 10 to the 7 meters per second. Now we know the de Broglie wavelength is h over momentum, or h over mv. We've got the mass of the electron from the sheet. We've got the velocity, we just worked it through. We know Planck's constant, so it's 1.7 times 10 to the minus 11 meters. Now, for diffraction to take place, the gap size must be equivalent to the actual wavelength of the object, in this case the de Broglie wavelength. So the spacing is going to be approximately 1.74 times 10 to the minus 11 meters for the diffraction to take place. The next question says, electrons exhibit wave-like behavior. Calculate the wavelength in meters of an electron with a speed of 2.09 times 10 to the 6 meters per second. Discuss whether the electrons with the wavelength in the previous question will be diffracted by a thin piece of graphite. Then, in an electron diffraction experiment, electrons accelerate at speeds that produce diffraction by a piece of graphite. In an electron diffraction tube, rings are produced on a screen. Describe and explain the effect of decreasing the potential difference through which the electrons are accelerated through on the rings produced. So pause the video now, then unpause the video when you want to go through your answer. So in this first one, we've got to use the de Broglie wavelength because it's electrons showing wave-like behavior. So we do lambda is equal to h over mv, pop in all the values, we give them all in the question, so the wavelength is equal to 3.48 times 10 to the minus 10 meters. Now, what does this show us? The wavelength is of the same order of magnitude as the spacing of the atoms, so therefore you would get diffraction taking place because the spacing between atoms in graphite is about 10 to the minus 10 meters. Now, in the last one, what can we say? Well, decreasing the potential difference will decrease the momentum of the electrons because they'll have less energy, so therefore they will not have as much work done on them, so they won't be moving as fast. This will therefore increase the de Broglie wavelength of the electrons. So this will in fact make the diameter of the rings greater, but that will mean because the rings are more spread out due to diffraction, the brightness of the rings is decreased. Now the next question says, the neon lamp shown in a glass bulb filled with neon gas at low pressure. Now when in use, the neon gas between the electrodes emits electromagnetic radiation. Explain why this happens when there's an electric current between the electrodes. And then when light from the neon lamp is incident upon a metal surface, electrons with a maximum speed of 2.68 times 10 to the minus 5 meters per second are emitted from the surface. The table shows the work function of some of the metals. To deduce which metal the light is incident upon, the frequency of light from the neon lamp is 5.56 times 10 to the 14 Hertz. So pause the video now, then unpause the video when you want to go through your answer. Right, so what is going on to take place? Well, the electrical current is a movement of electrons between the electrodes. The electrons will then collide with the neon atoms, and then energy is transferred to the neon atoms and the internal electrons in that neon atom in the collisions. So they're then promoted to higher energy level states, or they become excited, we would say. Now after a short time, the electrons in the neon atoms will then return to their normal state or their ground state, and they will de-excite. So when electrons then return to the lower energy level, it will then emit a photon of electromagnetic radiation equivalent to the difference in energy levels, which is why it emits that radiation. Now in this next one, we know that the energy coming from the actual neon lamp is E equals HF. So you pop in all the values, so we've got F in the question. So the energy coming from the neon lamp is 3.69 times 10 to the minus 19 joules. Our maximum kinetic energy produced is a half mv squared. Now we've got the mass of the electron and we've got the velocity of the electron from previous parts of the question. We pop that all in, so we get 3.27 times 10 to the minus 20 joules. Remember, photons are pushed into the metal there, and then the electrons are emitted out of the metal. So remember, going in the energy is the photon, going out the energy is from the electron. Now we know that the work function is equal to the energy from the photon minus the kinetic energy of the electron. It's the difference between the two values. So it's 3.69 times 10 to the minus 19 minus 3.27 times 10 to the minus 20. That gives us 3.36 times 10 to the minus 19 joules. When we refer to the information given in the question about the different elements, that must therefore be cesium. So that brings an end to our revision session today. If you've been successful and you've learned in this revision session, you should be able to answer A-Level Physics exam style questions, assess your understanding on A-Level Physics, and understand what topics you need to improve upon for AQA A-Level Physics. So thank you so much for watching this revision session for AQA A-Level Physics on Paper 1 for the topic of particles, in particular particle physics and quantum physics. Thank you so much and have a lovely day. Hello and welcome to this revision session for particles in AQA A-Level Physics Paper 1, in particular quantum physics. So, if we've been successful and we've learned in today's revision session, we should be able to answer A-Level Physics exam style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? When you complete your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. And in this left hand side section, write down your work now and answers to the questions in the revision session. When you're doing this, make sure to write your answers in full sentences and show your full working out. Now in the right hand side section, what you should do is write down any bits of information which you find useful, any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. Now, how should you be revising for AQA A-Level Physics? Well, the first thing you need to do is to learn the key facts. Use revision guides, class workbook, student prep notes and a textbook to learn the key ideas of the course. Then test yourself. Use things like Caboodle, Seneca, knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. The third step is to practice. Use exam preparation books, homework books, study books, additional workbooks to answer exam questions and mark your own work. So this cycle of learn the key facts, testing yourself and practicing exam style questions are how you should be revising for AQA A-Level Physics. So what are the key facts to do with quantum physics? Well, the first thing to look at is the photoelectric effect. Now, in the photoelectric effect, the threshold frequency is the minimum frequency required for the photoelectrons to be emitted from the metal surface. How it works is that light is made from photons, and the energy of one photon is equal to E equals hf. Now, the work function is the minimum energy needed to release an electron from a metal surface, and the stopping potential is the voltage needed to stop the most energetic photoelectrons. Now, the photoelectric equation is hf is equal to the work function plus the maximum kinetic energy of the emitted photoelectron. Now, in terms of collisions with electrons with atoms, ionization is when an electron gains enough energy to leave the atom completely. Excitation is when an electron moves to a higher energy level but stays within the atom. Now, fluorescent tubes show both excitation and ionization. Now, 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. When you have more collisions with electrons, what you must be aware of is line spectra. Now, that provides evidence of discrete energy levels in atoms. The photon emission equation is hf is equal to E1 minus E2, where E1 and E2 are energy levels. Now, energy released as a photon of light occurs when an electron moves from a higher to a lower energy level. For wave-particle duality, electron diffraction provides evidence that particles have wave-like properties. The photoelectric effect provides evidence that the electromagnetic waves have particle-like properties. Now, the de Broglie wavelength is lambda is equal to h over mv, where h is the Planck constant and mv is the momentum of the particle. Now, the diffraction pattern produced will widen if the momentum of the particle decreases. So, let us have a look at some questions to do with quantum physics. So the first question is, what is the photoelectric effect? So, pause the video now, then unpause the video when you want to go through your answer. The photoelectric effect is the emission of electrons from the surface of a metal when electromagnetic radiation is shined upon it. What does the photoelectric effect prove about the nature of electromagnetic radiation? So, pause the video now, then unpause the video when you want to go through your answer. The photoelectric effect proves that electromagnetic radiation must act like particles. What two effects prove that electromagnetic radiation must act like particles in the photoelectric effect? So pause the video now, then unpause the video when you want to go through your answer. The emission of photoelectrons is instantaneous, and the intensity of the radiation does not affect whether electrons are emitted or not. What does the intensity of the electromagnetic radiation affect in the photoelectric effect? So pause the video now, then unpause the video when you want to go through your answer. The intensity of the electromagnetic radiation affects the number of electrons emitted when the frequency is above the threshold frequency. What does affect whether photoelectrons are emitted? So pause the video now, then unpause the video when you want to go through your answer. The frequency of the radiation affects whether photoelectrons are emitted. What is the work function? Pause the video now, then unpause the video when you want to go through your answer. It is the minimum energy required to release an electron from the metal. What provides the energy to overcome the work function? So pause the video now, then unpause the video when you want to go through your answer. The photons provide the energy to overcome the work function. What assumption is made about the work function? Pause the video now, then unpause the video when you want to go through your answer. It is that the electrons are at the surface of the metal. What is the threshold frequency? Pause the video now, then unpause the video when you want to go through your answer. It is the frequency required to give the photons enough energy to overcome the work function. Where does any excess energy delivered by the photon above the work function go to? So pause the video now, then unpause the video when you want to go through your answer. The excess energy goes to the kinetic energy of the emitted photoelectrons. What would happen if a metal received electromagnetic radiation at the threshold frequency? So pause the video now, then unpause the video when you want to go through your answer. The photoelectrons would be emitted, but they would not be moving. What effect would increase in the frequency of the electromagnetic radiation when above the threshold frequency have on the photoelectrons? So pause the video now, then unpause the video when you want to go through your answer. The photoelectrons will be emitted travelling at a greater speed. How many photons are absorbed by an electron at one time? So pause the video now, then unpause the video when you want to go through your answer. One photon is absorbed at a time by an electron. Why do electrons in the metal have a work function? So pause the video now, then unpause the video when you want to go through your answer. Well, the work function is due to the attraction between the electrons and the positively charged ions found in the metal. What effect would increase in the intensity when above the threshold frequency have on the speed of the emitted electrons? So pause the video now, then unpause the video when you want to go through your answer. The intensity of radiation will not affect the speed, only the number of photoelectrons emitted. Why is the kinetic energy calculated in the photoelectric effect a maximum value? So pause the video now, then unpause the video when you want to go through your answer. The kinetic energy of the photoelectrons must be a maximum value as our work function is a minimum. Why are photoelectrons emitted with a range of speeds? Pause the video now, then unpause the video when you want to go through your answer. Not all electrons are at the surface of the metal, and the electrons dissipate some energy as they travel to the surface of the metal. How can the kinetic energy of emitted photoelectrons be measured practically? So pause the video now, then unpause the video when you want to go through your answer. You would place a potential difference next to the surface. This turns the kinetic energy of the electrons into electrical potential energy, and the electrons stop moving. This can be measured. On a kinetic energy frequency graph, what is the y-intercept of the straight line? Pause the video now, then unpause the video when you want to go through your answer. The y-intercept is the work function of the metal surface. On a kinetic energy frequency graph, what is the gradient of the straight line? Pause the video now, unpause the video when you want to go through your answer. The gradient is the Planck constant. On a kinetic energy frequency graph, do the gradients vary for different metals? Pause the video now, unpause the video when you want to go through your answer. All metals have the same gradient on the kinetic energy frequency graph, as the gradient is a constant value. It's the Planck constant. On a kinetic energy frequency graph, what is the x-intercept of the straight line? Pause the video now, then unpause the video when you want to go through your answer. The x-intercept is the threshold frequency. What would happen if a metal received electromagnetic radiation at the threshold frequency? Pause the video now, unpause the video when you want to go through your answer. The photoelectrons would be emitted, but they would not be moving after emission. On a kinetic energy frequency graph, why do all the straight lines have the same gradients for all metals? Pause the video now, then unpause the video when you want to go through your answer. Well, the gradient of the line is a Planck constant, and this is the same for all metals, as Planck's constant is a constant. What is the stopping potential? Pause the video now, then unpause the video when you want to go through your answer. The stopping potential is the potential difference needed to stop the fastest moving electrons travelling with kinetic energy. The next question says, what would happen to the stopping potential if the frequency of the photons is decreased? So, pause the video now, unpause the video when you want to go through your answer. Right, so the lower the frequency of the photon, the lower the kinetic energy the photon has. This gives a lower value of kinetic energy in the electrons, as the work function is fixed. This means a lower stopping potential is needed to stop the electrons. On the following diagram, what is the energy needed to excite an electron from the ground state to the valence shell due to photon absorption? Pause the video now, unpause the video when you want to go through your answer. The valence state is the highest energy level, so that's energy level 4. So it is the difference from energy level 4, 9 eV, to the ground state, which is energy level 1, which is 2 eV, so the answer is 7 eV. On the diagram, what is the energy needed to excite an electron from shell 3 to shell 4 due to a colliding free electron? So pause the video now, then unpause the video when you want to go through your answer. It is 9 eV minus 6 eV, so it is 3 eV. On this diagram, what is the energy needed to ionize an electron from shell 2? So pause the video now, then unpause the video when you want to go through your answer. It would be the ionization level, 15, minus the energy from shell 2 for 11 eV or more, because anything above that will still cause ionization. On this diagram, what is the energy needed to ionize an electron from shell 3? So pause the video now, unpause the video when you want to go through your answer. It's 15 eV minus 6 eV, so there's 9 eV or more. On this diagram, what is the energy needed to excite an electron from shell 2 to shell 4 due to photon absorption? So pause the video now, then unpause the video when you want to go through your answer. It will be 9 eV minus 4 eV, and it must be exactly 5 eV for this to take place. For this atom, what would happen if a PD of 2 volts was passed through it, and why? So pause the video now, then unpause the video when you want to go through your answer. The current would dip, as 2 eV would either cause an electron to be excited from level 1 to level 2, or from level 2 to level 3. This means that the kinetic energy of the electrons in the current will be lower, as energy has gone from the electrons in the current to excite the electrons in the atom, so you get a dip in the value of current. For this atom, what will be observed with an ammeter if a PD of 13 volts was passed through it, and why? So pause the video now, then unpause the video when you want to go through your answer. Nothing would happen to the current, as 13 eV will cause a ground state electron and all the other electrons to be ionized. This means that the kinetic energy of the electrons moving in the current would remain constant, so no difference would be observed. On this diagram, what are the possible energies which excite electrons without causing ionization? Pause the video now, then unpause the video when you want to go through your answer. From the ground state, you can excite at the following energies: 2 eV, 4 eV, and 7 eV. From shell 2, you can excite at the following energies: 2 eV and 5 eV. From shell 3, 3 eV, and from shell 4, there's no possible excitations that don't lead to ionization. From the following diagram, what is the energy needed to excite an electron from shell 2 to shell 3? Pause the video now, then unpause the video when you want to go through your answer. The answer is minus 8 eV minus 5 eV, leading to 3 eV, which is a positive value as the electron is moving to a less negative level. From the following diagram, what energies can be supplied to the atom to ionize it? So pause the video now, then unpause the video when you want to go through your answer. The possible ionization energies are 15 eV or more, 8 eV or more, 5 eV or more, or 2 eV or more. From the following diagram, what energies can be supplied to excite the electrons from shell 3? So pause the video now, then unpause the video when you want to go through your answer. The only possible excitation from shell 3 is to shell 4, so therefore it's -5 minus 2 eV, which is 3 eV. From the following diagram, what energies can be supplied to excite the electrons from shell 2? So our electron can be excited from shell 2 to shell 3, so -8 minus 5 is 3 eV, and then from shell 2 to shell 4, -8 eV minus 2 eV, which is 6 eV. From the following diagram, what energies can be supplied to excite the electrons from shell 4? So pause the video now, then unpause the video when you want to go through your answer. There is no possible excitations from shell 4, only ionization is possible. From the following diagram, at what voltages would current dip if a current was passed through a gas of this atom? So pause the video now, then unpause the video when you want to go through your answer. Current dips when excitation occurs. So for energy level 1, excitation will occur at 7 volts, 10 volts and 13 volts. At shell 2, or energy level 2, it would be 3 volts and 6 volts. For energy level 3, excitation occurs at 3 volts. From the following diagram, what energies can be supplied to the atom to ionize it in joules? So pause the video now, then unpause the video when you want to go through your answer. The possible ionization energies are -2.4 times 10 to the minus 18 joules or more, -1.3 times 10 to the minus 18 joules or more, -8 times 10 to the minus 19 joules or more, and -3.2 times 10 to the minus 19 joules or more. So let's have a look at some questions regarding quantum physics. The first question says, a research team is testing different metal surfaces to optimize solar charge and efficiency in a prototype space drone. They illuminate a clean metal surface in a vacuum with monochromatic UV light and measure the maximum kinetic energy of photoelectrons. The light used has a frequency of 1.15 times 10 to the 15 Hz, and the intensity is kept constant. The data below shows the results for the 3 different metals. Use the data for material A to estimate the work function of the metal in joules. Conclude whether this material will be suitable for use in a system where the threshold energy needs to be as low as possible. Determine whether the photon energy used in the experiment is sufficient to liberate electrons from material C. Then the engineer suggests that the increase in the intensity of the UV light could cause electrons to be emitted from material C. Evaluate this suggestion. So, pause the video now, then unpause the video when you want to go through your answer. Right, in our first one, we know that E equals HF. So we pop in our values, we see it's 7.6245 times 10 to the minus 19 joules. We know 1.5 EV is 2.4 times 10 to the minus 19 joules. Therefore, we know the work function is HF minus KE. So it's going to be 7.62 times 10 to the minus 19 minus 2.4 times 10 to the minus 19, which is 5.22 times 10 to the minus 19 joules. So our work function is a moderate value, not the lowest, so not ideal where very low threshold energy is required, so another material could possibly be better. In our next one, we know E equals HF. Once again, that's 7.6245 times 10 to the minus 19 joules. Now, no photoelectrons are emitted when the photon energy is less than the work function. So this tells us that the work function must be greater than this value, 7.62 times 10 to the minus 19 joules. So therefore, a work function must be greater than 4.76 EV. So our photon energy is not sufficient, regardless of the intensity of the emission, or so of the light being hit onto the metal surface. Finally, increasing the intensity increases the number of photons which hit the electrons per second, but not the energy per individual photon. If the photons still have energy below the work function, no electrons will be emitted from the surface. So the suggestion is incorrect. Frequency must increase, not intensity, to eject electrons from material C. An airport security company is developing a new sensor that relies on the photoelectric effect to detect high energy radiation emitted by hidden materials. The system uses a photoemitter surface and records the maximum kinetic energy of emitted electrons when exposed to radiation of varying frequencies. The graph below shows the experimental results for the sensor material. Use the graph to estimate the value of the Planck constant in SI units. Show your reasoning and comment on whether the results support the validity of the photoelectric equation. A security supervisor suggests that increasing the intensity of the incoming radiation at a frequency of 4.5 times 10 to the 14 Hz will cause electrons to be emitted. Suggest if the suggestion is valid or not. Finally, explain why this sensor would not function reliably when the visible light from typical airport lighting. Suggest one practical design feature that could reduce the risk of false readings from ambient light sources. So, pause the video now, then unpause the video when you want to go through your answers. So, how do you answer this question? Well, in the first one, we've got to be aware that the gradient of the line is the Planck constant. So you would do 2.5 eV over 7.8 times 10 to the 14 minus 4.8 times 10 to the 14. So our answer is 8.33 times 10 to the minus 15 eV. We could then convert that into joules by times by 1.6 times 10 to the minus 19. So therefore, we get our answer to be 1.33 times 10 to the minus 33 joules. Now the result is reasonably close to the accepted value, so therefore it supports our quantum photoelectric equation. Next, what we can say is that the graph shows that the threshold frequency, which is the x-intercept, must be 4.8 times 10 to 14 Hz. So therefore radiation at 4.5 times 10 to 14 Hz is below the threshold. No emission occurs regardless of intensity. Increasing intensity will increase the number of photons, not their individual energy, so the suggestion is incorrect. Finally, visible light frequencies tend to be less than 7.5 times 10 to the 14 Hz. So the graph shows frequencies only greater than 4.8 times 10 to the 14 Hz produces electrons. So this indicates to us that the visible light may be near the threshold, which could cause some false positives. So we could use a UV filter or shielding to block visible light, ensuring only the higher frequency radiation reaches the detector. A manufacturer is testing photocells that will be used in deep space telescopes to detect UV emissions from distant objects. In one test, monochromatic UV light of known frequency is shone on a clean metal surface in a vacuum. A variable potential difference is applied in the reverse direction to reduce the flow of photoelectrons. The current stops completely when the stopping potential is set to 1.80 volts. The frequency of the UV light is 9 times 10 to the 14 Hz. Calculate the work function of the metal in joules. Conclude whether this metal will be suitable for detecting lower frequency UV sources in space. A second experiment uses UV light of a slightly higher frequency, but the stopping potential remains the same. Discuss what this suggests about the energy the photoelectrons emitted and whether this result is expected. Suggest one possible reason why the stopping potential that was measured in A1.2 did not increase. Explain how an experimental or physical factor could have led to this outcome. So pause the video now, then unpause the video when you want to go through your answer. Right, in our first one, we know that EVS is equal to the kinetic energy, where Vs is 1.80, the stopping potential. So therefore our kinetic energy is 1.8 times by 1.6 times 10 to the minus 19. So it's 2.88 times 10 to the minus 19 joules. We know HF, we can work it through to be 5.97 times 10 to the minus 19 joules. Therefore, our work function is the two values subtracted from each other, which is 3.09 times 10 to the minus 19 joules. So again, it's a moderate work function, not ideal for low frequency UV, so it might actually miss some distant sources. Next, we know higher frequency means a higher photon energy, so normally it will expect a higher kinetic energy of the emitted photoelectrons. Now, the stopping potential is unchanged, which implies to us that the kinetic energy of the emitted photoelectrons has not increased. This suggests that the emitted electrons are losing energy before they are escaping. So this is unexpected in the ideal photoelectric conditions, so indicates that possibly that the electrons are colliding with something as they're leaving the metal surface. Now, one reason why it might not have took place as well is that there's surface contamination or oxidization, reducing the effective energy transfer. Or the detector might have a potential measurement error. The practical limitations or the surface effects may influence the results and not actually the photon energy. A company is designing an energy-efficient light source for a tropical fish aquarium. The engineers are experimenting with using a fluorescent discharge tube containing mercury vapor. Electrons accelerated through a potential difference of 11 volts collide with mercury atoms inside the tube. These collisions excite mercury atoms, which then emit UV photons as they de-excite. A phosphor coating inside the tube absorbs the UV and re-emits visible light. Calculate the maximum energy in joules that an electron gains from the 11-volt potential difference. Conclude whether this energy is sufficient to excite an electron in a mercury atom from the ground state to the first excited state. Some emitted photons have an energy of 4.9 eV, whilst others correspond to transitions from higher levels, such as 6.7 eV and 10.2 eV to the ground state. Use this data to explain why a phosphor coating is required to make the tube produce visible light. An engineer suggests using argon instead of mercury because argon atoms emit photons at a single energy level of 1.8 eV. Evaluate whether this would be suitable for producing visible light without a phosphor coating. So pause the video now, then unpause the video and you want to go through your answer. Right, in our first one, we know that the value is equal to EV. So we convert our EV into joules. So we get 1.76 times 10 to the minus 18 joules. We then convert 4.9 EV into joules. So 7.84 times 10 to the minus 19 joules. 1.76 times 10 to the minus 18 is greater than 7.84 times 10 to the minus 19. So the energy is therefore sufficient to excite electrons to the 4.9 EV level. Next, we know that the 4.9 eV, 6.7 eV and 10.2 eV photons are emitted. We can work out the wavelengths for each one, 254 nanometers, 186 nanometers and 122 nanometers. All correspond to roughly UV wavelengths, which are invisible to the human eye. So a phosphor coating would be needed to absorb this UV and re-emit it in the visible range. Finally, we know E equals lambda over hc, so lambda is equal to 690 nanometers. Now 690 nanometers is in the visible red spectrum, so therefore it tells us that no UV is emitted, phosphor would not be needed. However, single energy emission would produce monochromatic red light, which probably wouldn't be suitable for illuminating an aquarium. Astronomers analysed the emission spectra of light passing through exoplanet atmospheres during transits across their parent stars. Specific emission lines suggest that which atoms are present. In one observation, a scientist detects a prominent spectral line at 121 nanometers and later observes additional weaker lines at 102 nanometers and 656 nanometers. The telescope's onboard database provides the following information about energy levels relative to the ground state in the hydrogen atom. Identify which energy level transitions could have produced each of the three spectral lines observed. Explain why the 121 nanometer line is the most intense, while the 102 and the 656 nanometer lines are weaker even though the transitions occur in the same atom. Then discuss the limitations of using visible light spectroscopy alone to determine the composition of distant planetary atmospheres. So, pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, when we work it through by doing E equals hc over lambda, E will be approximately for 121 nanometers be 10.2 eV, for 102 nanometers be 12.1 eV, and for 656 nanometers 1.9 eV. So therefore 121 will correspond from n equals 2 to n equals 1, 102 will correspond to n equals 3 to n equals 1, and 656 corresponds from n equals 3 to n equals 2. Now the intensity depends on the probability of the transition and how populated each of the states are. Now most electrons will relax from N2 to N1, which will be the most common transition. Higher transitions like 3 to 1 are less populated, so there are fewer photons emitted. Now 656 comes from 3 to 2, a less frequent transition leading to weaker lines. Now, many key transitions fall outside the visible range. Now, in addition, atmospheric absorption and telescope sensors may limit the detection of non-visible light photons. So the visible light alone will give an incomplete data on the atmospheric composition of the exoplanet. A group of scientists is conducting an experiment using an electron diffraction tube. When electrons are fired at a thin layer of graphite, a circular diffraction pattern appears on the fluorescent screen. The team reduces the accelerating voltage applied to the electrons and observes that the spacing between the diffraction rings increases. They discuss whether this supports the idea that electrons behave like waves and whether this might influence our understanding on the nature of matter. Explain how the observed changes in the diffraction pattern provide evidence for the wave nature of electrons. Include in your answer a discussion of how the momentum of the electrons affects the pattern. Discuss how the idea of wave-particle duality has influenced the development of models of matter. Include reference to how scientific theories are reviewed and accepted by the wider scientific community. Evaluate why the demonstration of electron diffraction in a lab experiment is considered strong evidence for the quantum model of the electron rather than just a curious visual effect. So, pause the video now, then unpause the video when you want to go through your answer. In our first one, diffraction is a wave phenomena. The particles produced in diffraction implies that it's wave behavior. The larger ring spacing at lower voltages means that the electrons are diffracting more. A lower voltage gives a lower speed, which gives a lower momentum. From de Broglie's hypothesis, the lower momentum gives a larger wavelength. Now, therefore, this tells us that wavelength affects the diffraction pattern, which supports our wave-particle duality. Now, duality challenged classical physics and required new quantum models. It provided an explanation for phenomena like electron diffraction and the photoelectric effect. Now, theories must always undergo peer review and experimental validation. The wider spread acceptance followed repeated confirmations in independent experiments. Finally, the diffraction pattern is consistent and predictable. It's not a random effect. It can only be explained by electrons having a wavelength, supporting the quantum theory. So this confirms that matter exhibits wave behavior. A team of engineers is testing a new electron microscope that relies on the electron diffraction to probe the structure of crystalline materials. The system allows fine control over the accelerating voltage, and the resultant diffraction pattern is measured on a detector screen. They record the distances between the central bright spot and the first diffraction ring, called the fringe radius, at various accelerating voltages. Describe and explain the trend in fringe radius as the accelerating voltage increases. One member of the team claims that the results prove that electrons are waves. Evaluate this claim using both the data and your understanding of quantum physics. The microscope is being marketed as capable of detecting features smaller than the wavelength of visible light. Assess whether this claim is realistic. So pause the video now, then unpause the video when you want to go through your answer. Right, in our first one, as the voltage increases, the fringe radius decreases. The higher voltage means the electrons gain more kinetic energy, so are moving faster. The de Broglie wavelength, lambda equals h over mv, increasing velocity means shorter wavelength. The shorter wavelength means less diffraction, leading to a narrower ring pattern, and the trend is consistent with wave-like behavior predicted by quantum mechanics. Now, the data shows predictable diffraction patterns, which is wave behavior, but electrons also show particle behavior, such as the photoelectric effect. So the result supports wave-particle duality, not that electrons are only waves. The claim is too simplistic. Evidence supports a dual nature, not a pure wave idea. Finally, as the voltage increases, the de Broglie wavelength decreases, so our resolution improves. The visible light wavelengths 400 to 700 nanometers, the electron wavelengths at these voltages are much shorter. So the claim is realistic. Short electron wavelengths will enable higher resolution imaging. So that brings an end to our revision session today. If we've been successful and we've learned in this revision session, we can answer A-Level Physics exam style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for A-Level Physics. So thank you for watching this video on particle physics, which is part of AQA A-Level Physics Paper 1. Thank you so much and have a lovely day. Hello and welcome to this revision session for AQA A-Level Physics Paper 1 on the topic of particles and radiation. So if we're successful and we learn in this revision session, we should be able to answer examination questions for A-Level Physics Paper 1 on the particles and radiation topic. So if we've been successful and we've learnt in today's revision session, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for our A-Level Physics in the particles and radiation topic. So how should you prepare for this revision session? Well, when you're completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left-hand side larger than the right-hand side. In this section, write down your work and out and answers to the questions in the revision session. When you're doing this, make sure you write your answers in full sentences and show your full working out. Whilst on the right hand side, write down any bits of information which you find useful, any hints and tips on answering questions from this revision session. At the end of this revision session, write up these notes into a revision sheet for you to use independently. Now, how should you be revising your A-Level Physics? The first step is to learn the key facts. So use the revision guides, class workbook, student prep notes and the textbook to learn the key ideas of the course. You might wish to make mind maps or write out notes yourself. The second step is to test yourself. So use the Caboodle e-learning platform, the Seneca e-learning platform, student knowledge checkers to quickly test your own knowledge. And you may wish to do this from your own cue cards. The third step is to practice examination questions. So use exam prep books, homework books, supervised study books, additional workbooks to answer examination questions and mark your own work. And you may wish to download your own examination past papers to do this. So the 3 steps of learn the key facts, testing yourself, and then practicing examination questions are how you should be revising for your A-Level Physics. Now, in this revision session, there'll be 3 types of questions. The first type are general check questions. These are basic questions designed to probe your understanding of the key concepts of the topic. The second are the checkpoint questions. These are more challenging questions designed to place your knowledge and understanding of the topics into different contexts and applications. And the final ones are the assessment point questions. These are past paper examination questions which will mimic the type of questions found in public examinations. So let's now have a look at some questions for particles. So the first question says, calculate the energy of a photon of frequency 4.0 times 10 to the 18 Hz. The microwave region of the electromagnetic spectrum is considered to have wavelengths ranging from 5 mm to 50 cm. Calculate the range of microwave photons. And then in a microwave oven, photons of energy 1.02 times 10 to the minus 5 eV are used to heat food. Express 1.02 times 10 to the minus 5 eV in joules. Calculate the frequency of the photons and calculate the wavelength of the photons. So pause the video now, then unpause the video when you want to go through your answer. Right, we've got to remember that the equation to work out the energy of the photon is E equals hf, where h is Planck's constant, which is 6.63 times 10 to the minus 34, so we get 2.7 times 10 to the minus 15 joules. The other way to work out the energy of a photon is to say E equals hc over lambda, where c is the speed of light, or 3 times 10 to the 8. Pop in all the values and you get it from 4 times 10 to the minus 23 joules to 4 times 10 to the minus 25 joules. Remember, you convert 5 millimeters into meters and 50 centimeters into meters as well. Now, the conversion factor from EV into joules is multiplying by 1.60 times 10 to the minus 19. Again, you are given that conversion value on your examination sheet. So the value will be 1.63 times 10 to the minus 24 joules. We can rearrange our previous equation, say F equals E over H, pop in all the values and we get 2.46 times 10 to the 9 Hz. Then to calculate the wavelength of the photons, again, we can use the equation C equals F lambda. That can work for photons as well. So lambda equals C over F, pop the values in and we get 0.12 meters. The next question says, list all of the positive quarks, state the quark combination for the proton and the neutron, compare baryons and mesons, and then what is the antiquark combination of the antineutron. So pause the video now, then unpause the video when you want to go through your answers. Right, you've got to be aware that there's 6 types of quarks and they come in 3 generations. 1 quark from each generation is a positive and 1 quark from each generation is a negative. So the 3 positives are the up, the charmed and the top, with the 3 negatives being the down, the strange and the bottom. Now you've got to remember and memorize the quark combination for the proton and neutron. The proton up up down, the neutron down up down, or dud, because the neutron has no charge. Now if we're comparing baryons and mesons are hadrons and are made from quarks, and then baryons have 3 quarks whilst mesons have 1 quark and 1 antiquark pair. Now baryons and mesons, as they're both hadrons, will both experience the strong interaction. Now what's the antiquark combination of the antineutron? Well, it's the antiquarks of the neutron seen above, so it's anti-down, anti-up, anti-down. The next question says, determine the charge of the following hadrons. The kaon positive and the pion 0, or the neutral pion. Then the second question is, a hadron named Z was discovered in the Large Hadron Collider in Geneva in 2014. It has the quark combination charmed, anti-charmed, down and anti-up. So determine the charge of this particle. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first one, you've got to remember that you can look on your equation sheet and you'll see what the values of the charge should be for individual quarks. Now remember, the antiquark will have the opposite charge of the quark, and also remember, as well as a hint, because it's K positive, it's going to be a +1. So the quark is plus 2/3, the anti-strange is plus a third, so it's overall plus a 1. Now remember, particles have to have integer values of charge in this particular unit. Now for the pi 0, it's going to be plus 2/3 minus 2/3, so the value is 0. And then here we can see that the charmed has a value of a positive 2/3, the anti-charmed is a minus 2/3, the down is minus a third, the anti-up is minus 2/3, so the overall value is minus 1. The next question says, figure 30.18 shows another energy level diagram. In this case, energies are given in electron volts. From the list below, state which photon energies could be absorbed by such an atom. 6 eV, 9 eV, 11 eV, 20 eV, 25 eV, 34 eV, or 45 eV. So pause the video now, then unpause the video when you want to go through your answer. Right, for this question, you've got to remember, if there's an energy level difference, then you'll actually get an absorption of a photon. So you'll notice that there are 9 eV, 11 eV, 25 eV, 34 eV, 20 eV, and 45 eV all correspond to differences between energy levels, so they can all be absorbed. But 6 eV does not correspond to any differences between the energy level values, so therefore cannot be absorbed. The next question says, the line spectrum for a particular type of atom is found to include the following wavelengths: 83 nanometers, 50 nanometers, 25 nanometers. For each one, calculate the corresponding photon energies in eV, and then sketch the energy level diagrams which could give rise to these photons. On the diagrams, indicate the corresponding electron transitions responsible for these three spectral lines. So pause the video now, then unpause the video when you want to go through your answers. Right, you've got to remember, to work it out, you will firstly use the equation E equals hc over lambda, because we're given lambda, and we know h and c because they're constants. We convert our nanometers into meters because it's times 10 to the minus 9, and for each one as well, to go from joules into eV, you divide by 1.6 times 10 to the minus 19, so you get 15 eV, 25 eV, and 50 eV from the calculation shown on the screen. So what that means is, for your energy transitions, you're going to need a particular diagram which would actually have these different transitions. So you'll need a 50 eV, you will need a 25 eV, and you'll need a 15 eV transition to actually get those particular out. Now again, remember, they're going down because they're being emitted, and emission is when they drop down the levels. The next question says, figure 30.17 shows part of the energy level diagram of an imaginary atom. The arrows represent three transitions between the energy levels. For each of these transitions, calculate the energy of the photon, calculate the frequency and wavelength of the electromagnetic radiation, and then state whether the transition contributed to an absorption or an emission spectrum. So pause the video now, then unpause the video when you want to go through your answer. Right, now again, for each one you can work out the following. So you can say that the energy of the photon is the difference in energy between the energy levels. Now remember, in the diagram you saw before, it's times 10 to the minus 18 joules. So you just got to use that conversion in there. So if the first one is 5.6 times 10 to the minus 18 joules, then to work out the frequency, it's this energy divided by h. So you get that one 8.4 times 10 to 15 hertz. Then the wavelength is going to be c over f. So this one's 3.6 times 10 to the minus 8 meters, and we know it's emission because the electron is dropping down energy levels. You do the same for photon B, and you get 5 times 10 to the minus 19 joules, 7.5 times 10 to 14 hertz, and 4 times 10 to the minus 7 meters, with it being emission. Now for photon C, it's 2.2 times 10 to the minus 18 joules, then to 3.3 times 10 to 15 hertz, and then 9 times 10 to the minus 8 meters, with it being absorption as the electron goes up the energy levels. The next question says, X-rays are used to find out about the spacings of atomic planes in crystalline materials. Describe how the beams of electrons could be used for the same purpose, and then how might electron diffraction be used to identify a sample of a metal. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you've got to remember that electrons can behave as waves due to wave-particle duality, so they can be diffracted as a wave would be by the spaces between the atoms. Now, each metal will have a different lattice structure, so it'll have a different distance between the atoms, so it'll produce a different diffraction pattern. Now the next question says, a beam of electrons is accelerated from rest to a PD of 1 kilovolt. What is the energy in eV of each electron in the beam? Calculate the speed and then the momentum of each electron. Calculate the de Broglie wavelength of each electron. And would you expect the beam to be significantly diffracted by a metal film in which the atoms are separated by a space of 0.25 times 10 to the minus 9 meters? So pause the video now, then unpause the video and you'll want to go through your answer. Right, remember in this first one you can convert from kilovolts into EV for electrons because it's an electron volt by just saying it's actually going to be 1000 EV because it'll just work through, so it's 1k EV, because remember an electron which is accelerated through a potential difference of 1 kilovolt will lead to have an energy of having 1 kilo electron volt. Now the next one, we can say that, well, kinetic energy equals a half mv squared. We know what the kinetic energy is from the previous question because we'll just convert that 1 keV into joules. So therefore we can work it through by saying V equals the square root of 2 Ek over m. Pop in all the values. The mass of the electron is given to you on the equation sheet, 9.11 times 10 to the minus 31. So you get 1.9 times 10 to the 7 meters per second. Our momentum is mass times by velocity. We've just worked out the velocity. We know the mass, so it's 1.7 times 10 to the minus 23 kilograms meters per second. Now we know the de Broglie wavelength equation, you're given this in your exam, is lambda equals h over mv. H being the Planck's constant. We've just worked out the momentum, mv, before, so it's 3.9 times 10 to the minus 11 meters. Now that tells you that that's much smaller than 1.25 times 10 to the minus 9 meters. It's out by about a factor of 1, so therefore it's much smaller than the spacing, so there'll only be a small amount of diffraction. Right, the next question says, in 2022, CERN announced the discovery of a new particle known as a pentaquark, which is made of 5 quarks. The table shows the charges on some quarks. The 5 quarks in the pentaquark are C, C, D, S and U. Some scientists say that the pentaquark is made of a meson and a baryon, held together by the attraction of their equal yet opposite charges. Determine the quark combination and the charge of a meson and of a baryon that could make up the pentaquark. So pause the video now, then unpause the video and you'll want to go through your answer. Right, in this question you've got to be aware of what's a meson. A meson is 1 quark, 1 antiquark, and a baryon is going to be 3 quarks. Now you've got to remember that they're going to have to make an integer value of a charge, okay, and they're going to have to cancel each other through. So what you're going to have to do is, for the meson, it's going to be an anti-charmed, and it's going to be one of the quarks from C, D, S or U to then work it through, to then give out your value there of minus 1. Then you're going to have 3 quarks from your C, D, S or U. Again, we're going to try and get a combination give us plus 1, so the 2 will ultimately cancel through. The next question says, a nucleus of rhenium-187 decays to a nucleus of osmonium by emitting a beta particle. Complete the nuclear equation for the decay of rhenium-187, and then the electron released to the decay is 2.6 keV. You may assume that in this case the beta particle receives all the emitted energy. Calculate the speed of the beta minus particle emitted in this decay. So pause the video now, then unpause the video and you want to go through your answer. Right, in this first one, you've got to remember the beta minus particle is an electron, so it's going to have a value of 0 on the top and minus 1 on the bottom. Now, the numbers on the top have to all add together. So 187 before equals 0 plus another value, which is 187, and then 75 before equals minus 1 plus 0 plus another value, which is 76. So in this next question, you can convert your energy from keV into joules by using your conversion factor. We can then say that is the kinetic energy. We can then say that therefore equals a half mv squared. So therefore we can work out V and we get our value to be 3.02 times 10 to the 7 meters per second. Once again, you're given the mass of the electron on the equation sheet. The next question says, pions belong to a group of particles known as mesons. State the quark structure of mesons. Then mesons belong to a family of particles known as leptons. State one property of leptons. Then the charged pions usually decay into a muon and another particle X, as shown by this decay equation. The student suggests that X is an anti-neutrino due to particle conservation laws. Deduce whether the student is correct. So pause the video now, then pause the video when you want to go through your answer. Right, in this first one, it's just knowledge. A meson is a quark and antiquark. Now, you've also got to know the properties of leptons. That's just facts. So, leptons are fundamental. They can't be broken down any further into smaller particles. They've got a non-zero lepton number, so it's either plus 1 or minus 1, and a baryon number of 0. You could also say that they'll experience the electromagnetic and weak interaction, but not the strong interaction. Now in this next one, you've got to work out the conservation. So because the charge of the pion minus is going to be -1 and the muon there is -1, well, it tells the the x value must be 0. The lepton number of the pion is 0, and we know the muon has a lepton number of +1, so therefore the x must have a lepton number of -1. And therefore the baryon number of the pion is 0, the baryon number of the muon is 0, so therefore x must have a baryon number of 0. That fits the properties of an antineutrino, so that is correct. The next question says, hadrons are groups of particles. Write a detailed account of hadrons, including how they may be subdivided into other groups of particles, given examples. Then, a high energy interaction between a proton and a pion is shown below. Use conservation laws to show that the interaction is possible. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question you've just got to know lots of key facts about hadrons. So hadrons are made from quarks. These hadrons and quarks will feel the strong interaction. Hadrons can be split into two groups. That'll be the meson, okay, which are made of one quark, one antiquark, and baryons, which are made of three quarks. The most common type of baryon are the protons and the neutrons. Protons, two quarks, so two up quarks, one down quarks. The neutron, one up, two down quarks. You'll know that you can work out the overall charge of them, so the proton to be +1 and the neutron to be 0. Mesons will be that one quark, one antiquark. You can have pions if they don't contain a strange quark, but kaons if they do contain a strange quark. And we're going to have three generations of therefore quarks, which are up, down, top, bottom, and charm strange, whilst hadrons have a lepton number of 0, baryons have a baryon number of 1, antibaryons -1, and mesons will be 0. Now in this next one, you've got to show your conservation laws. So you can see that the charge before is +1 and -1, so it's 0 overall, and then afterwards it's 0 +1 -1, so therefore it's 0 afterwards. That is possible. The baryon number 4 is 1 + 0. Then afterwards it's 1 + 0 + 0, so that is conserved. 1 before equals 1 after. And then all the values, all the particles there are not leptons, so they've all got a lepton number of 0. So all three are conserved. The next question says, the proton-antiproton collider was a large particle accelerator. An experiment using this proved the existence of a particle called the Z boson. The mass of a Z boson is 91 GeV/c². Show that the mass of the Z boson is nearly 100 times greater than that of the mass of the proton. Protons and an antiproton were accelerated in the particle accelerator to very high energies before they collided. Explain why the protons and antiprotons needed high energies to produce the Z boson. And then Z bosons produced by high energy collisions can have a range of lifetimes. The Z bosons with the longest lifetime are those that were moving very fast. Explain this observation. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we've got to convert our GeV/c² into kilograms. So you do that by converting GeV into joules by doing 10 to the 9, which is giga, times by 1.6 times 10 to the -19. Then you divide it by 3 times 10 to the 8 squared, because it's c squared, so we get 1.62 times 10 to the -25 kilograms. We then divide that by the mass of the proton, 1.67 times 10 to the -25, a value given to you on your examination sheet, so it's 97 times the mass of the proton. Now you need the high energies to do this because we know mass energy is conserved in a particle interaction. So therefore, if we need to create a particle of high mass, we need high energy before that collision to produce it. So therefore, this mass for this larger particle, the Z boson, is coming from the kinetic energy of the colliding particles. Now the particles that have the longest lifetime are those moving very fast, because when you move close to the speed of light, you'll have a relativistic increase in your in the lifetime of it due to the theory of relativity. Now the next question says, ultraviolet light is instant on a zinc plate. If the photon energy is greater than the work function of the zinc, electrons are released. State firstly what is meant by the work function. The ultraviolet section of the electromagnetic spectrum can be split into three parts, known as UVA, UVB, UVC. The range of wavelengths of these parts is given in the table. The minimum de Broglie wavelength of the released electron is 1.50 times 10 to the -9 meters. The work function of zinc is 4.30 eV. Deduce whether the UV light incident upon the zinc plate is UVA, UVB, or UVC. Then the student used a zinc plate and UV light of different frequencies in an experiment. The student's graph of maximum kinetic energy of the released electrons against the frequency of the incident UV is shown. Einstein's photoelectric equation applies to the situation. Describe two ways that the graph is not consistent with values known for a zinc plate. Your answer should include calculations. So pause the video now, then unpause the video when you want to go through your answer. Firstly, you've just got to memorize what the work function is, and it is the minimum, and that's very important to use the word minimum, the minimum energy required to release electrons from the surface of a metal via the photoelectric effect. Now, which one is it? Well, you can use your equation of saying that lambda equals h over p, which p is the mv, so it's just the de Broglie equation. So we can work out what the momentum is. So it's 4.42 times 10 to the minus 25 kilogram meters per second. We then say, well, momentum is mass times by velocity. So velocity is momentum over mass. So we work that through and we get 4.85 times 10 to the 5 meters per second. We know that kinetic energy is a half mv squared, so we pop the value for v in. We know the mass of an electron is given to us on the equation sheet, so it's 1.07 times 10 to the minus 19 joules. That's our kinetic energy of the electron. We then convert the work function into joules by multiplying the value in EV by 1.60 times 10 to the minus 19 joules, okay, and then you work it through, okay, to be 6.88 times 10 to the minus 19 joules. We then say E equals HF plus a half mv squared to work out the total energy of the photon, so we get 7.95 times 10 to the minus 19 joules. Frequency is therefore E over H, so you divide that then by Planck's constant to get 1.20 times 10 to the 15 hertz. Finally, we can work out the wavelength by doing lambda equals c over f, where c is the speed of light. So we work it through to be 2.5 times 10 to the minus 7 meters, which is 215 nanometers, which is going to be UVC. Okay, and then finally, on this question, how is it not appropriate? Well, firstly, the y-intercept should be a negative value, and you can see that the y-intercept's about minus 10 eV, much greater than any value that it could be for zinc, given from the previous question. Again, the threshold frequency is your x-intercept, which you can see on the graph to be about 7.5 times 10 to the 14 hertz. It should be about 1 times 10 to the 15 hertz if you look at the values given before, so it can't be zinc. And then finally, the gradient of the line should be Planck's constant. It should be 6.63 times 10 to the minus 34. You work it through, and it's actually 2.1 times 10 to the minus 33, so it can't therefore be that particular value. So the next question says, in an experiment to demonstrate the photoelectric effect, ultraviolet light is incident on a metal plate. Photoelectrons are released from the plate with a maximum speed of 3.51 times 10 to the 5 meters per second. Calculate the energy of these photoelectrons in EV. Then the table shows typical values of the work function for 4 different metals. The ultraviolet light used in the experiment has a wavelength of 310 nanometers. Deduce which of the metals was most likely to be used as the metal plate. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this one, what you've got to do is you say, right, well, the kinetic energy is a half mv squared, and we know that the mass is that of the electron, which we're given on the equation sheet. So you pop all the values through, and you get the energy in joules to be 5.60 times 10 to the minus 20 joules. You then divide that by 1.6 times 10 to the minus 19 to get the answer to be 0.35 eV. So we can then say, well, the total energy is hc over lambda. We've got lambda, it's 310 times 10 to the minus 9, because nanometers into meters. So we get 6.42 times 10 to the minus 19 joules. So we can then say, well, the overall value of the work function is going to be hf, which we've just worked through, minus the half mv squared, which we know about before. So we convert that 0.35 eV into joules, so it's 5.6 times 10 to the minus 20 joules. We know that the total energy is 6.42 times 10 to the minus 19 joules, so it's 5.86 times 10 to the minus 19 joules, which when you look across must be magnesium. The next question said, photons are only emitted from a given metal surface if the frequency of the incident radiation is above a particular value. Explain why. Then the student makes the following statement. It does not matter what the value of the work function is for a particular metal. Photoelectrons can always be released if the intensity of the incident light is high enough, so criticize the student's statement. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, it's important to know that in the photoelectric effect that each photon will only interact with one electron at a time, and the electrons absorb energy from the photons, or the photons transfer energy to these electrons. So the minimum energy required for the electron to be emitted is that work function, which actually must be lower than the photon energy transferred to the electron. So the higher photon energy is from the higher frequency, because E equals hf. So when the energy is above the work function, the electron is emitted. Now the statement can't be right below, because the intensity of the incident light relates to the number of photons which are hitting the surface per second. So therefore it is related to the number of photoelectrons emitted per second, but the intensity does not affect the energy of the photon, okay, or then the photoelectron emitted. So therefore it doesn't affect whether an electron can overcome that work function and be emitted from the material. The next question says, figure 30.28 shows 5 of the energy levels in a helium ion. The lowest energy level is known as the ground state. Firstly, calculate the energy in joules that's required to completely remove the remaining electron originally in its ground state from the helium ion. Then calculate the frequency of the radiation which is emitted when the electron drops from n equals 3 to n equals 2. State the region of the spectrum in which the radiation lies in, and then without further calculation describe qualitatively how the frequency of radiation emitted when the electron drops from n to 2 compares with that of the radiation emitted when it drops from 3 to 2. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you've just got to look at the difference from the ground state up until 0. So therefore it's 54.4 eV. Turn that into joules by multiplying by 1.6 times 10 to the minus 19, and it's 8.7 times 10 to the minus 18 joules. This next one, to see the energy emitted, you've got to find the difference in the two energy levels. So you get 7.5 EV. You can then say F equals E over H, but remember that's only if E is in joules. So you convert the EV first into joules, divided by Planck's constant, and it's 1.8 times 10 to 15 Hertz, which you should know lies in the ultraviolet region. Then finally, you can see that from the values given that the drop in energy from n equals 2 to n equals 1 is much more than that from 3 to 2, because you can tell from the difference in the energy level values are given in the diagram. So therefore the frequency of the light emitted must be much higher, because the frequency of the radiation links directly to the energy. The next question says, the spectrum of the sun has dark lines. These dark lines are due to the absorption of a certain wavelength by the cooler gases in the atmosphere of the sun. One particular dark spectral line has a wavelength of 510 nanometers. Calculate the energy of a photon with this wavelength. Explain the significance of the energy levels having negative values, and then explain, with reference to the energy level diagram above, how a dark line in the spectrum may be due to the presence of helium in the atmosphere of the sun. Then all the light absorbed by the atoms in the sun's atmosphere is re-emitted. Suggests why a dark spectral line of wavelength 590 nanometers is still observed from the Earth. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, the first one you've got to do is use your photon energy equation, but we've already been given the wavelength, E equals hc over lambda, convert nanometers into meters by times 10 to the minus 9, so the value is 3.4 times 10 to the minus 19 joules. It's important to know why they have negative values. It's because we say the electrons have zero potential energy at infinity when they're released from the atom, so therefore they've got to have put energy in to get to zero, so they start off as a negative value. Now you can see that in the next question the electron's excited from the minus 5.8 times 10 to the 19 joules level to the minus 2.4 times 10 to the minus 19 joule level. So it absorbs all that energy level of the instant photon. And then why would it still be observed from the Earth? Because this instant light is then directional and is re-emitted in all directions. The next question says, figure 30.30 shows 3 of the energy levels in an isolated hydrogen atom. The lowest energy level is known as the ground state. Explain what happens to an electron in the ground state when it absorbs energy from a photon energy 21.8 times 10 to the minus 19 joules. Explain why a photon is emitted when an electron makes a transition between energy levels n equals 3 and n equals 2. Calculate the wavelength of electromagnetic radiation emitted when an electron makes a jump between the n equals 3 and n equals 2. And in the diagram, each energy level is labelled with its principal quantum number n. Use the energy level diagram to show that the energy E of an energy level is inversely proportional to n squared. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, well, if it goes from this ground state and it absorbs the energy, well, it's going to actually be completely removed from the nucleus because it'll have enough energy to actually get to the nucleus and then to get to the top of the atom and then leave, so it'll be totally removed from that atom. Now, what's happening is that we know that when it's going downwards, well, then the potential is less than the n equals 2 than 3, so therefore energy must be given out in the form of a photon. That's the principle of line spectra. And then to work out the jump, you work out your change in energy level, so it's going to be 3 eV. Convert that into joules by multiplying by 1.6 times 10 to the minus 19. You then say lambda equals hc over E, work it through to be 4.1 times 10 to the minus 7 meters. And then this next one is just shown about the idea of inverse proportionality. So if E is directly proportional to 1 over n squared, well, therefore E n squared equals a constant. So for each energy level, do E times by n squared. They all come out at approximately the same value, minus 21.6, proving that they're inversely proportional. The next question says, Sirius A is the brightest star in the night sky and is mostly composed of hydrogen. When light from Sirius A passes through the hydrogen in the outer layers of the star, some of the light is absorbed. This causes the electrons in the hydrogen to be excited. The diagram shows an electron being excited from the minus 3.40 eV level to the minus 1.50 eV level. The wavelengths of the different colours of visible light are shown in the table below. Deduce the colour of the visible light that caused the electron transition shown in the diagram. So pause the video now, then unpause the video when you want to go through your answer. So the first thing you do in this question is look at what the difference is in the two energy levels, and it's 1.9 eV. You then multiply by 1.60 times 10 to the minus 19 to get it into joules. 3.0 times 10 to the minus 19 joules. You can then say, well, frequency is E over H, so you divide it by Planck's constant to get the frequency out. We can then say the wavelength is C over F, where C is the speed of light. We can use C because it's a photon, so therefore traveling at the speed of light. So we get the value to be 6.54 times 10 to the minus 7 meters, which is going to be about 654 nanometers, because you can go up by 2 because we're going to minus 9 from minus 7. So therefore the light, when you look at the table, must be red. The next question says, the diagram shows the energy levels for an atom of hydrogen. An electron is in the ground state, minus 13.6 eV level of this atom. A photon interacts with this electron. Explain why this interaction caused the emission of another photon. Then a photon has a wavelength of 280 nanometers. Determine the energy in eV of this photon. Then explain whether the atom of hydrogen could emit a photon with this energy. So pause the video now, then unpause the video when you want to go through your answer. Right, it'll cause an emission because we know that the electron is going to move to a higher energy level when it's been absorbed, when it's had energy absorbed into it. Therefore, it will drop back down after it's been excited. When it de-excites and goes back down, it will release a photon. Now in this next one, we know that from the question, we know V equals F lambda. So we know that F is going to be V, which is 3 times 10 to the 8 because it's a photon, divided by the wavelength, which is 218 times 10 to the minus 9 because we go from nanometers to meters. We can then say E equals HF. So we plug in the value of F, which we just worked out, and we can work out our E to be 9.12 times 10 to the minus 19 joules. We then divide by 1.60 times 10 to the minus 19 to get our value in EV, 5.70 EV. Now, could the atom of hydrogen emit a photon with this energy? Well, there's no difference of 5.7 eV in those energy level diagrams of hydrogen, so it's not possible for this photon to be emitted. Now, the next question says, explain what is meant by the wave-particle duality of electromagnetic radiation. Then explain how the photoelectric effect gives the evidence for this phenomena. Then the figure shows the maximum kinetic energy of the emitted photoelectrons as the frequency of the incident radiation on a sodium plate is varied. Explain why there are no photoelectrons emitted when the frequency of the incident light is less than 5.6 times 10 to the 14 Hz. Calculate the work function of sodium and use the graph to calculate the value of Planck's constant in joule seconds. So pause the video now, then unpause the video when you want to go through your answer. Well, the first one is just a definition. The wave-particle duality is the idea that electromagnetic radiation displays both wave-like behaviour and particle-like behaviour. The photoelectric effect indicates that you can only release radiation, okay, above a certain frequency, the threshold frequency. So, and then at that point, the energy of the photoelectrons will increase with that frequency, indicating that they are receiving the energy in a particular packet, which is a photon, which is when they're exhibiting particle behavior. Now, there are no photons emitted below that frequency because the energy of the photon will be less than the work function, the minimum energy needed for an electron to be emitted from the surface of the metal. So therefore, it won't actually be emitted below that point. The work function, well, we know we can look at the graph, and that on the graph, the threshold frequency is 5.6 times 10 to 14 hertz. Therefore, E equals HF. So we can work out the work function, the energy equivalent of the threshold frequency, by multiplying the frequency by Planck's constant. So we get 3.7 times 10 to the minus 19 joules. And then on this graph, the gradient of the straight line is Planck's constant. So you work out the gradient of the line, and we get 6.6 times 10 to the minus 34 joule seconds. The next question says, the table below shows the work function of 4 metals. The electromagnetic radiation of wavelength 380 nanometers is incident on all the metals. Photoelectrons are just emitted from metal A. Explain in terms of photons why metal C will not emit photoelectrons. Then calculate the maximum wavelength of the electromagnetic radiation in nanometers that will just eject photoelectrons from metal D, and then metal B is now exposed to the electromagnetic radiation of a different wavelength. The energy of each instant photon is 5.3 eV. Calculate the minimum de Broglie wavelength of the emitted photoelectrons. So pause the video now, then unpause the video when you want to go through your answers. Right, so it won't emit photoelectrons because the energy of the photon is less than the work function. So when you work it out, the energy of doing E equals hc over lambda, and then working it through in joules, then working out the value of it in eV by dividing by 1.6 times 10 to the minus 19, the energy is less than the work function. Now, what's the maximum wavelength? Well, what you'll do is you'll work out to be 190 nanometers, but what you'll do is you'll say, right, well, E equals hc over lambda, so lambda equals hc over E. So the E value is going to be just enough to overcome the work function, so 6.4 eV, which you convert 6.4 eV into joules by doing 6.4 times 1.6 times 10 to the minus 19, so you get 190 nanometers. Now, we can see here that we know that the kinetic energy is going to be the total energy, which is 5.3, minus the work function, which from the table is 4.1. So therefore, overall is 1.2 eV. So we can therefore work out what the velocity is going to be by then popping into the kinetic energy equation. But remember, we convert the 1.2 eV into joules by times and by 1.6 times 10 to the minus 19. So we work it all through, and lambda is 1.1 times 10 to the minus 19 meters. The next question says, pions are created in the upper atmosphere when high energy cosmic rays interact with nuclei. Pions are mesons and they quickly decay to muons. Muons are leptons with a mass of 106 MeV over c squared. Give the possible quark structure of a pion. Then the equation shows a pion decaying into a muon and an antineutrino. The energy and momentum must be conserved in this decay. Explain 2 of the conservation laws that will apply to this decay, and then calculate the mass in kilograms of a muon. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, pion can't contain a strange quark because it would therefore be a kaon if it wasn't. You can see what's the structure of a pion. Well, it's got to add up to either an integer of +1, -1 or 0. So you can have the up anti-down, up anti-up, or down anti-down. Now in this next one, you just got to top up those conservation laws, and the 3 you've got to remember are the conservation of charge, the conservation of lepton number, the conservation of baryon number. Now you can see the charges on the top. It's easy, and remember, neutrino, neutral, okay, has no charge. The lepton numbers, you've got to remember that if it's a meson, it doesn't have a lepton number. A normal lepton will have a value of +1, and an anti-lepton, such as the antineutrino, will have a -1, and none of them are baryons, so they're all 0. This next one, you convert your mass from MeV over c squared into kilograms by multiplying the EV out, the MeV out into joules by doing 10 to the 6 times by 1.6 times 10 to the minus 19. We can then divide it by 3 times 10 to the 8 squared for c squared, so you get 1.88 times 10 to the minus 28 kilograms. The next question says, describe the interaction that is responsible for keeping protons and neutrons together in a stable nucleus. You should include the details of the properties of the interaction in your answer. Nuclei can decay by alpha decay and beta decay. In alpha decay, only one particle is emitted, but in beta decay, there are two emitted particles. Explain how baryon number is conserved in alpha and beta decay. The kaon decays by the weak interaction. The equation shows an example of kaon decay. State one feature of this decay that shows us an example of the weak interaction. And then there have been considerable advances in our understanding of particle physics over the past 100 years. Explain why it is necessary for many teams of scientists and engineers to collaborate in order for these advances to be made. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, it's due to the strong interaction. That's a fact you've got to remember. Now, it's got a short range, or it's got a traction up to 5 femtometers. It's got repulsion up to about a distance of 1 femtometer or below, and it's negligible beyond 5 femtometers. The strong interaction only affects hadrons, or baryons and mesons, or things made from quarks, and is mediated by the pion or the gluon exchange particle. Now, in alpha decay, we know that the numbers of neutrons and protons are unchanged because there's 2 protons, 2 neutrons leaving an atomic nucleus, so therefore the baryon number is unchanged. In a beta decay, the neutron changes to a proton. They're both got the same baryon number, so it is conserved, and it will also produce an electron and antineutrino. Okay, or the other way around, it'll produce an anti-electron, which is a positron, and a neutrino, and in this instance they will both have 0 baryon numbers, so it can ensure the baryon number is decayed. We know that this decay is an example of the weak interaction because strangeness is not conserved. Strangeness is only conserved in strong interactions, not weak interactions. And finally, we've got to understand for particle physics that the results of the experiments in particle physics have to be independently checked or peer reviewed before they're accepted. Particle accelerators are very expensive, and collaboration helps spread the cost of building them. And then we've got lots of data to process, and we need many skills and disciplines to do this. The next question says, students investigated the photoelectric effect. They used a piece of magnesium ribbon placed inside the cylinder of a copper gauze as shown. There was an air gap between the copper gauze and the magnesium ribbon. The copper gauze was connected to the positive terminal of a power supply. The magnesium ribbon and the sensitive ammeter were connected to the negative terminal of the power supply as shown. The students made the following observations. When the light from an ultraviolet lamp was incident on the gauze and ribbon, a current was detected in the ammeter. When the polarity of the power was reversed, the current decreased to 0. Explain these observations. Then the student reconnected the circuit so that a current was detected when ultraviolet light was incident on the gauze and the ribbon. The students replaced their original light with an ultraviolet lamp with a much greater intensity. Explain the effect this had on the experiment. And then the ultraviolet lamp was replaced by a laser which emitted red light of wavelength 633 nanometers. To deduce whether the photoelectric effect would occur, the work function of magnesium is 3.7 eV. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first one, you'll notice that the photons of the ultraviolet light will cause the photoelectrons to be emitted from the surface of the magnesium ribbon. Now, this occurs because the photon energy of from the ultraviolet light is greater than the work function of the magnesium, because the frequency of the ultraviolet light E equals HF, therefore gives a value of energy greater than the work function, or you could just say the frequency is greater than the threshold frequency of magnesium. Now, electrons are always attracted to the positively charged gauze, so therefore will move and create a current. So when the polarity is reversed, the current goes to 0 because the electrons won't have enough kinetic energy to move across the gap because they're now being repelled by the negative charge on the gauze now, so they'll want to stay on the other side. Now, what effect would this have? Well, you'll notice that the photons are already being emitted by the circuit. So a greater intensity will mean there are more photons hitting the surface every second. So therefore there are more electrons being being removed from the metal surface per second. So therefore there's a greater rate of flow of charge. The value on the ammeter goes up. Now in this next question, we've got the wavelength, so we can work out the frequency of the light by doing F equals c over lambda. C is the speed of light because it's a photon. Therefore, we can work out the frequency. We can say E equals HF, and we work it out to be 3.14 times 10 to the minus 19 joules. So therefore, we can work that out by saying, well, we can look at the work function and put that into joules, and times 3.7 eV by 1.6 times 10 to the minus 19. Compare the two factors. The energy of the photon is less than the work function, so the photoelectric effect will not take place. The next question says, the Planck constant is an important universal constant used in the study of wave-particle duality. In the demonstration of the photoelectric effect, ultraviolet radiation with a frequency of 2.8 times 10 to the 16 Hz is instant on the surface of clean zinc. Electrons are released from the surface of zinc. Calculate the maximum velocity of the released electrons. The work function of zinc is 6.9 times 10 to the minus 19 joules. Atomic electrons are confined within the atom. One model of the atomic electron suggests that the wave associated with an atomic electron forms a standing wave that fits in with the diameter d of the atom. The diagram shows the lowest frequency standing wave that fits into the diameter of the atom. Calculate the momentum of the electron with d equals 2.00 times 10 to the minus 10 meters. Then electrons in an atom can only exist at discrete energy levels. Explain how this standing wave model can account for this. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one, you can say, what's the kinetic energy? Well, the kinetic energy is going to be equal to the energy of the photon, which is hf. So you've got F in the question, 2.8 times 10 to the 16, times by Planck's constant, minus the work function in joules, which we're given to be 6.9 times 10 to the minus 19. So we've got our kinetic energy. We're going to then say V equals the square root of 2 EK over M. Just rearrange the kinetic energy equation. We know the mass of the electron now. We use the mass of the electron because it's the electron's kinetic energy we've got, so therefore it's 6.26 times 10 to the 6 meters per second. This next one, we can work out the momentum because we know the de Broglie wavelength is the Planck's constant over mv, which is the momentum. So we can rearrange it. We can make the momentum the subject, and we get 1.67 times 10 to the minus 24 kilogram meters per second. Now in this last one, how can the standard model account for this? Well, we know with the standing wave, it can only occur in discrete numbers. It can only occur when you've got half wavelengths. So therefore, a discrete number of half wavelengths fit into the diameter of the atom, and therefore they link to the energy levels, and that's why you get discrete energy levels, because in standard waves, they can only occur at particular frequencies called harmonics, so they will then convert into the different standard wave values. The next question says, the picture shows an electron diffraction pattern produced by graphite in a cathode ray tube. Describe the experiment that produces this pattern. Draw a labeled diagram of the apparatus to help you. Explain why the light and dark circles as shown in the picture are produced, stating what this evidence provides about electron behavior. A potential difference of 5 keV is used to accelerate the electrons. Calculate the work done on the electrons. Calculate the de Broglie wavelength of the accelerated electrons and suggest a value for the space in between the graphite atoms just to find your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, how would you do this experiment? Well, you need to be able to get electrons to the graphite. So you'd have in an evacuated tube where there's no air, the electrons are released by thermionic emission, so you heat up the surface to release electrons by ionization. We then will put them in an area where they will accelerate, so you go through a potential difference, so they're accelerated towards an anode by an electrical field. They then will hit the graphite target and diffract through. Remember, it has to be graphite 1 atom thick to get a nice clear diffraction pattern, and the electrons are then detected on the screen as shown. Now the light and dark circles will provide evidence for the wave nature of the electrons, because the light circles are produced by the electrons diffracting, which is a wave property, and then having constructive interference, so the waves arrive in phase producing a light circle there, and dark circles are caused by destructive interference where the waves from the different electrons arrive out of phase or in antiphase. Now the work done, we can link that into, you're looking at the idea of just converting that into joules. So it's turning kilovolts into joules. So remember, 5 kilovolts gives you an energy of 5 kiloelectron volts because there's electrons being accelerated. So you convert that into joules by multiplying it by 1.6 times 10 to the minus 19. So you get 8 times 10 to the minus 16 joules. The de Broglie wavelength is, well, you know what that the work done is a half mv squared. So you can work out what the values that's going to be by doing a half times by mass, which you're given on the equation sheet, times by the velocity squared. Work that through to get V, which is 4.2 times 10 to 7 meters per second. We're going to say the wavelength for the de Broglie is the Planck's constant over mv. You've got all the other values. You pop in the value of V you've worked through, and it's 1.7 times 10 to the 11 minus 11 meters. Now, for diffraction, the gap size needs to be approximately the same as the de Broglie wavelength, should be equal to approximately that value, 1.74 times 10 to the minus 11 meters. The next question says, electrons exhibit wave-like behavior. Calculate the wavelength in meters of an electron with a speed of 2.09 times 10 to the 6 meters per second. Discuss whether the electrons with this wavelength will be diffracted by a thin piece of graphite, and in an electron diffraction experiment, electrons are accelerated at speeds that produce diffraction by a piece of graphite. In an electron diffraction tube, rings are produced on a screen. Describe and explain the effect of decreasing the potential difference through which the electrons are accelerated through on the rings produced. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first one, we know that the de Broglie wavelength is h over mv. Pop in all the values and we get 3.48 times 10 to the minus 10 meters. Now, would that actually cause diffraction? Well, yes, it would do, because that wavelength is approximately the order as the spacing of that of atoms. You should know it's about 10 to the minus 10 meters, so therefore it would work through. Now, in the next one, if you decrease the potential difference, the momentum of the particles will be less because they've got a lower velocity, so therefore the de Broglie wavelength, lambda equals h over mv. If mv goes down, well then lambda will go up, so therefore the rings will have to have a greater diameter, but because they're more spread out, the brightness will be less. The next question says, the neon lamp shown is a glass-filled bulb with a neon gas at low pressure. When in use, the neon gas between the electrodes emits electromagnetic radiation. Explain why this happens when there's an electrical current between the electrodes. Then when the light from the neon lamp is incident upon a metal surface, the electrons with a maximum speed of 2.68 times 10 to the 5 meters per second are emitted from the surface. The table shows the work function of some metals. Deduce which metal is the light incident upon us, and the frequency of the light is 5.56 times 10 to the 14 hertz. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, how does it work? Well, the electrical current is a movement of the electrons between the electrodes. Those electrons collide with the neon atoms. In that collision, the electrons transfer energy to the neon atoms. That makes the electrons in the neon atoms be excited to higher energy levels. So therefore, after a short time, they'll then de-excite back down to their normal state. When the electrons in that neon then de-excite, that will emit a photon of electromagnetic radiation. Now in this next question, we've got the frequency, so we can work out the photon energy, so E equals hf, and we get E to be 3.69 times 10 to the minus 19 joules. We can know that the kinetic energy is a half mv squared. We've got the idea that it's going to be a half times by the mass of the electron times by the velocity given in the question, so therefore it's 3.27 times 10 to the minus 20 joules. We know that the work function is therefore going to be the photon energy minus this kinetic energy, so we get the work function to be 3.36 times 10 to the minus 19 joules, and looking on the table, that is cesium. So that brings an end to our revision session today. So hopefully, if you've been successful and you've learned in this revision session, you should be able to answer A-level physics examination questions, assess your understanding on A-level physics, and understand what topics you need to improve upon for A-level physics in particles and radiation. So I hope you've enjoyed this revision session on the particles and radiation topic for AQA A-Level Physics. Thank you so much, and have, as always, a lovely day. Hello and welcome to the following particles and revision session for AQA A-Level Physics. So in today's revision session, we're going to look at trying to answer examination questions on A-Level Physics for particles and radiation. So if we've been successful and learned in this revision session to be able to answer examination questions for particles and radiation, assess our understanding on A-Level Physics for particles and radiation, and finally understand what topics we need to improve on for AQA A-Level Physics. So in preparation for this revision session, on the piece of paper in front of you, divide your piece of paper into two sections. Make the section on the left hand side larger than that on the right hand side. In the left hand side section, write down your working out and answers to the questions we cover in this revision session. And when doing this, try to write your answers in full sentences and show full working out. Whilst in the right hand side, write down any bits of information in this section which you find useful, or any hints and tips on answering the questions you've gained from this revision session. Then after the revision session ends, write up these notes in a revision sheet for you to use independently. So let's start off with some multiple choice questions. In this question, radon, francium and radium are three nuclides. How many neutrons does each nuclide have in its nucleus? So pause the video now, then unpause the video when you want to go through your answer. Now what you've got to remember is the number of neutrons is your atomic number, which is the number at the top, minus, the mass number, which is the number at the top, minus the atomic number, which is that at the bottom. So you do 211 minus 86, 210 minus 87, and 212 minus 88. So it gives us our biggest number for B. Next question, which nucleus has a smaller value of specific charge than the nucleus oxygen? So pause the video now, then unpause the video when you want to go through your answer. So to work out the specific charge, it's the ratio of protons to the number of nucleons, because it's the charge to mass ratio, with the protons providing the charge and the protons and neutrons providing the mass. So instead of having to work out the specific charge for each one, just do the ratio of the atomic number to the mass number. So 3 to 7, 5 to 11, 6 to 13, and 17 to 37. And the only one smaller than 8 to 18 is B. Next question. When bombarded with an alpha particle, the nuclide of magnesium changes into another nuclide with the emission of a neutron and gamma radiation. What are the correct values for the nucleon number and the proton number of the nuclide which is formed? So pause the video now, then unpause the video when you want to go through your answer. So the alpha particle will increase the proton number by 2 and the nucleon number by 4, because an alpha particle is 2 protons, 2 neutrons. The emission of a neutron will decrease the nucleon number by 1, but not affect the proton number. So it will increase the nucleon number by 3 and the proton number by 2. So the answer is C. Next question. A calcium ion is formed by removing 2 electrons from an atom of calcium. What's the specific charge of the calcium ion? So pause the video now, then unpause the video when you want to go through your answer. So specific charge is the charge to mass ratio. Now to work out your charge, you multiply your relative charge by 1.6 times 10 to the minus 19. Then to work out the overall mass in kilograms, multiply the relative mass by 1.67 times 10 to the minus 27. Again, in this level of detail for significant figures, you don't need to differentiate between the masses of the protons and the neutrons. So it gives us our answer of D. Next question. Which of the following nuclei has the smallest specific charge? So pause the video now, then unpause the video when you want to go through your answer. So the specific charge once again is the ratio of the number of protons to the number of nucleons. So it's 1 to 1, 6 to 12, 6 to 14, and 92 to 235. So this gives us an answer of D. Next question, what's the correct equation for the beta plus decay? So pause the video now, then unpause the video when you want to go through your answer. So the beta plus decay, by its name, beta plus, means there must be a positive beta particle produced, which is a positron, and when you produce a antilepton, you must also produce a neutrino to conserve your lepton number. So the answer is B. Next question, the nucleus of beryllium captures a proton and emits an alpha particle. What is the product nucleus? So again, pause the video now, then unpause the video when you want to go through your answer. So capturing a proton increases the proton and nucleon numbers by 1 each. Now emitting an alpha particle will decrease the nucleon number by 4 and the proton number by 2, because alpha is 2 protons and 2 neutrons, so 4 nucleons. So the overall change is a decrease in the nucleon number by 3 and a proton number by 1. So our answer is C. So next question. Thallium is an unstable nuclide in a radioactive decay series. It decays by emitting an alpha particle, and the next 2 nuclides in this series emit beta minus particles. What nuclide is formed after these 3 decays have taken place? So pause the video now, then unpause the video when you want to go through your answer. So again, emitting an alpha particle decreases the nucleon number by 4 and the proton number by 2. Now the beta decay will increase the proton number by 1 but not change the number of nucleons, because the beta decay is a neutron to a proton inside the nucleus. So overall the nucleon number decreases by 4 and the proton number stays constant. So our answer is D. Next question. Which sequence of radioactive emissions results in the formation of an isotope of the original element? So pause the video now, then unpause the video when you want to go through your answer. Right, so in alpha decay you lose 2 protons. Now we talk about protons only because that determines what element you have. Now a beta decay, which is a neutron to a proton, gains you a proton. So therefore 1 alpha decay, which where you lose 2 protons, and 2 beta decays where you gain 2 protons, will produce the isotope of the same element. So our answer is B. Next question, which equation shows the process of annihilation? So pause your video now, then unpause the video when you want to go through your answer. Right, Annihilation is when a particle and antiparticle interact to make two photons. So the only situation where that is exhibited in this particular answers is B. So our answer is B. Next question, which elementary particle is a lepton? So pause the video now, then unpause the video when you want to go through your answer. Right, so this again is rote knowledge. You should know that protons and neutrons, as they're made from quarks, are baryons, that quarks are found in baryons and mesons, so the only one which is a lepton is in fact an electron. So our answer is C. Next one, what of the following is a hadron of zero charge? So pause the video now, then unpause the video when you want to go through your answer. Right, so again, you've got to be aware of which one's a hadron. So firstly, the proton and the neutron are made from quarks, so it can be hadrons. The photon and the neutrino are not made from quarks, so cannot be hadrons. Now, out of the two of them, the neutron has no charge, so our answer is B. Next question, what are the numbers of hadrons, baryons and mesons in an atom of lithium? So pause the video now, then unpause the video when you want to go through your answer. Right, in this isotope you can see that there are 3 protons and 4 neutrons. You can tell that because the number on the bottom is 3, indicating the number of protons, so therefore the top number minus the bottom number, 7 minus 3, gives you your number of neutrons, which is 4. Now the neutron is a baryon and a hadron, the proton is a baryon and a hadron, so that tells us we've got 7 hadrons, 7 baryons and no mesons. Our answer is C. Let's look at the next question. Which line correctly classifies the particles shown? So pause the video now, then unpause the video when you want to go through your answer. Now you should hopefully be aware that a neutron is made from 3 quarks, D, U, D, down, up, down. Now the neutron is a baryon, not a meson, so therefore we're aware of that, and the positive pion has to be a down, anti-up, because to get the correct charge and baryon number for that particular meson. So the only one we can have is C, which is the correct answer. Now the next one, which of the following statements about muons is incorrect? So pause the video now, then unpause the video when you want to go through the answer. Now, muons will have a lower kinetic energy compared to the electrons because they've got to be moving slower to achieve the same momentum because they've got more mass. So therefore, as the velocity is squared in kinetic energy, EK is a half mv squared, there's a greater factor in kinetic energy, so therefore the electron is moving faster. So therefore, the only answer which is incorrect is in fact B. Next question, which of the following is not made from quarks? So pause the video now, then unpause the video when you want to go through your answer. So it's important to note that things made from quarks are called hadrons. So that tells us that only mesons and baryons can be made out of quarks. Now the neutron is a baryon, so it's made out of 3 quarks. The pion and the kaon are mesons, so they're made from 1 quark, 1 antiquark. A muon is a lepton, so therefore it's not made from quarks, it's fundamental. So the answer is B. Next one, what's the quark structure for antiprotons? So pause the video now, then unpause the video when you want to go through the answer. Right, now a proton has a quark structure of up, up, down, UUD. That's a fact you've got to remember. So an antiproton has the same quark types, but they're the anti-versions as the proton. So it's anti-up, anti-up, anti-down. Our answer is D. Next question. Electron capture can be represented by the following equation. Which row correctly identifies X and Y? So pause the video now, and then we'll go through the answer when you unpause the video. So, in electron capture, a proton turns to a neutron. You've just got to remember that fact. So if a lepton is present, there's got to be an antineutrino there to conserve the lepton number. So the only possible combination of the two which does this is C, so that's our answer. Next question, what interactions are involved in the production of a strange particle and its decay into non-strange particles? So pause the video now, then unpause the video when you want to go through your answer. Now, strange particles are called kaons. Now, they're produced via the strong interaction and decay via the weak interaction, which is why we observe them in the universe for longer after a collision than we should do. So our answer is therefore D. Next question. A beam of electrons is directed at graphite crystal. After passing through the crystal, the beam is incident on a fluorescent screen where each incident photon produces light. The photograph shows the pattern observed on the screen. So, which of the following gives the two properties of the electrons which help explain the production of this pattern? So pause the video now, then unpause the video when you want to go through the answer. So the pattern is produced is an interference pattern. Now we get interference patterns when you get diffraction and then superposition of the waves that have been diffracted. So therefore our answer is B, and in this case the electron is acting like a wave. Next question. Some of the energy levels of an atom of gas are shown, during which transition A, B, C or D is electromagnetic radiation with the shortest wavelength emitted. So pause the video now, then unpause the video when you want to go through the answer. So, firstly, photons are only emitted when electrons move down levels. Now, the equations for the energy emitted by a photon is E equals hc over lambda. So therefore, lambda is equal to hc over E. So the shortest wavelength comes from the greatest energy level transition, downwards, which is D. Next question. In the photoelectric effect, what is the relationship between the work function of a material and its stopping potential? So pause the video now, then unpause the video when you want to go through the answer. Now Einstein's photoelectric effect equation is E equals hf, which is equal to the work function plus the kinetic energy, a half mv squared. Now the stopping potential is equal to the maximum kinetic energy, so we can just remove that from the equation, and when we rearrange it we get our answer to be D. Next question. This graph shows the relationship between the maximum kinetic energy of the photoelectrons emitted from material X and the frequency f of the incident light. Which line of variation of kinetic energy with f for the different materials? So pause the video now, then unpause the video when you want to go through the answer. Now, the gradient of the line is Planck's constant, so it has to be unchanged from x. Now, the line can't be c, as the y-intercept needs to be a negative to gain a work function within the metal, because it's a negative value, because you've got to put energy into the metal to liberate the electrons. So our answer is D. Next question. Which graph shows the relationship between the de Broglie wavelength lambda of an electron and its kinetic energy? So pause the video now, then unpause the video when you want to go through the answer. So we know kinetic energy is equal to a half mv squared, so therefore lambda is equal to h over mv. So this means our two terms are linked by the equation 1 over x squared. Now our only graph which allows us to have this is the graph of C, and there's our answer. The next one, this diagram shows an atomic line spectrum. What's the minimum number of energy levels in an atom that could produce this spectrum? So pause this video now, then unpause the video when you want to go through your answer. Now there are 10 transitions shown on the atomic line spectrum, so this means there's got to be 5 levels, because you'll have 4 transitions from the 5th level, 5 to 4, 5 to 3, 5 to 2, 5 to 1. You'll have 3 transitions from the 4th, 2 from the 3rd and 1 from the 2nd, and obviously none from the 1st. So therefore our answer is B. The next one, photoelectrons may be emitted from a metal surface where electromagnetic radiation is incident on the metal surface. The graph shows the variation of kinetic energy of the emitted photoelectrons with the frequency. Which expression is equivalent to the Planck's constant? So pause the video now, then unpause the video when you want to go through your answer. So in a kinetic energy frequency graph, the gradient is Planck's constant. So this is given by the y over the x on the graph, which is the work function over the frequency, which is therefore going to give you the answer of D. Next question. A metal surface is illuminated with ultraviolet radiation. The number of photoelectrons emitted from a surface per unit time and the maximum kinetic energy of the photoelectrons are both measured. The illumination is now changed by increasing the frequency of radiation and decreasing the number of photons incident on the metal surface per unit time. Which row correctly describes the observed changes? So pause the video now, then unpause the video when you want to go through your answer. So increasing the frequency of radiation increases the maximum kinetic energy of the electrons, while decreasing the number of photons incident will decrease the number of electrons emitted. So our answer is A. Next question. A proton has a kinetic energy of 5 times 10 to the minus 12 joules. What's the de Broglie wavelength of the proton? So pause the video now, then unpause the video when you want to go through your answer. Now we know that kinetic energy is a half mv squared, so V is equal to the square root of 2 times kinetic energy over the mass. So you pop your values in, and because you know the mass of the proton from the equation given to you, 1.67 times 10 to the minus 27, you get a velocity of 7.7 times 10 to the 7 meters per second. Now we know the de Broglie wavelength is lambda is equal to h over mv. Now we know the mass of the proton from the back of the book. We've just worked out V, and Planck's constant is another constant you can get from the back of the book. So you work it out to be 5.13 times 10 to the minus 15 meters. Next question. The diagram shows the ground state and 2 excited energy levels x and y of an atom. The wavelength corresponds to each transition is shown. What's the energy level difference between x and y? So pause the video now, then unpause the video when you want to go through the answer. So the first thing you've got to say is E is equal to hc over lambda. Now lambda in this instance is going to be the difference between the two energy levels, because we're looking for the difference. So it's 121 nanometers minus 103 nanometers. Pop the values in and you get 1.1 times 10 to the minus 17 joules. Next question. An electron has a kinetic energy E and a de Broglie wavelength of lambda. The kinetic energy is increased to 4E. What is the new de Broglie wavelength? Pause the video now, then unpause the video when you want to go through your answer. So we know lambda is equal to h over mv. So when the kinetic energy is quadrupled, the velocity is doubled, because velocity is a square in the kinetic energy equation. So therefore it means to maintain our overall value, we're going to have to halve the wavelength. So the answer is B. Next one. In a photoelectric experiment, light incident on the metal surface of a photocell is then have an increased intensity of illumination. So what will then increase? So pause the video now, then unpause the video when you want to go through your answer. So when the intensity of the photons increases, there's going to be more electrons released every second, because one photon interacts with one electron, and we already know that it's already releasing the electrons because they've been illuminated. So therefore that increases the current of the circuit, because we can measure that as the movement of the electrons off the metal. So therefore our answer is C. Next question. An electron collides with a neutral atom and ionizes it. Which of the following describes the particles present after the collision? So pause the video now, then unpause the video when you want to go through the answer. So when ionization occurs, an electron is released and a positive ion is also formed. So this tells us that there's going to be an electron released and a positive ion remaining. But in addition to that, you're already going to have the original colliding electron, because that electron does not leave the universe. So as a result, we've got 2 electrons and we've now got a positive ion. So our answer is C. Next question. Monochromatic radiation from a light source, which we'll call source A, is shone on a metallic surface and electrons are emitted from the surface. When a second source B, is used, no electrons are emitted from the metallic surface. Which property of radiation from source A must be greater than source B? So pause the video now, then unpause the video when you want to go through your answer. Now there's only one factor which determines whether electrons are released from a metal surface: the frequency of radiation. That's just a fact, because E equals HF, so our answer is B. Next question. Electromagnetic radiation incident on a metal surface can cause electrons to be emitted. Which of the following statements is correct? So pause the video now, then unpause the video when you want to go through your answer. So only photons above the work function allow electrons to be emitted. Electrons differ in energy depending on where they are in the metal. So the range of emitted electrons depends on the frequency of the radiation. So our answer is D. Now the next one, the diagram here shows the 4 lowest energy levels for an electron in an atom. So P, Q, R and S represent the relative energy values of the energy levels. So an electron transition from R to Q is accompanied by the emission of a photon of visible light. Which electron transition will be accompanied by the emission of a photon of infrared radiation? So pause the video now, then unpause the video when you want to go through your answer. Now emission only occurs when the electrons move down the level, so anything up can't be the case, and infrared radiation is produced when the energy transition between the 2 levels is the smallest as possible, so our answer is going to be A, S to R. So that's a very important idea to work through. Now, next question. Experiments on which of the following suggest the wave nature of electrons? So pause the video now, then unpause the video when you want to go through your answer. So wave nature is shown by diffraction and interference. Now, line spectra and the photoelectric effect is evidence of the particle nature of light. So therefore, our answer is A. Next question. When light of certain frequencies greater than the threshold frequency of a metal is directed at the metal, photoelectrons are emitted from the surface. The power of the light incident on the metal surface is doubled. So which row shows the effect on the maximum kinetic energy and the number of photoelectrons emitted per second? So pause the video now, then unpause the video when you want to go through your answer. So, when the intensity of photons incident doubles, therefore the number of photoelectrons emitted doubles, because there's one photon absorbed by every electron. Now, the intensity of the photons doesn't affect the maximum kinetic energy, only the frequency does that, so therefore that remains unchanged. So our answer is going to be C. So we've now looked at some particles and radiation's multiple choice questions. Now let's do some general questions. So we're just going to look at some longer questions, more extended responses compared to the multiple choice. So in our first question, what we're going to do is we're going to look at the following. The apparatus shown in the figure below can be used to demonstrate the photoelectric effect. Photoelectrons are emitted from the metal cathode when it's illuminated with white light which has passed through a blue filter. So the intensity of the light source is reduced. State and explain the effect of this on the emitted photoelectrons. Secondly, explain why no photoelectrons are emitted when the blue filter is replaced by the red one. So pause the video now, then unpause the video when you want to go through your answer. Right, so in the first one, we can say that the intensity determines the number of photons per second. So therefore, there's going to be fewer photoelectrons emitted per second because it's a one-to-one interaction. One photon interacts with one electron. Now, the photon energies aren't changed, so therefore there's no change in the kinetic energy or speed of the emitted photoelectrons. Now, there's no photons emitted because the energy of a photon is proportional to its frequency, E equals hf. So a photon of red light has less energy than a photon of blue light because its frequency is lower, and this energy is insufficient to overcome the work function of the metal. Right, next question. Monochromatic light with a photon energy 3.7 times 10 to the minus 19 joules is incident on a metal surface. Photoelectrons with maximum kinetic energy of 5.7 times 10 to the minus 20 joules are emitted from the surface. Calculating EV, the work function of the metal. Then the total power of the monochromatic light incident on the surface is 1.3 times 10 to the minus 2 watts. Calculate the maximum number of photoelectrons that can be emitted from the surface per second. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, there's a few things you've got to do. So you've got to know that work function is equal to the total photon energy minus the kinetic energy. So you get 3.1 times 10 to the minus 19 joules. Now you then got to convert from joules into EV, and you do this always by dividing from joules by 1.6 times 10 to the minus 19, and that gives us our answer of 1.95 or 2 EV. Now you've got to think that the total power is going to be the energy of one photon times by the total number of photons emitted in 1 second. So therefore the total number emitted in 1 second is the total power divided by the energy of one photon. Now we're told the energy of one photon up above in the first part of the question, and we know the total power from the second one, so we divide one by the other and get 3.5 times 10 to the 16 joules. Next question. So define the electron volt. Then an electron in a vacuum is accelerated from rest through a potential difference V, so that the final speed V of an electron is given by V equals 5.9 times 10 to the 5 times by the square root of the potential difference. Then an electron is accelerated from rest through a potential difference of V, which is equal to 5 kilovolts. To calculate the minimum de Broglie wavelength for the electron. Then accelerated electrons can be used to produce diffraction patterns. Electron diffraction patterns were first observed in 1927. So discuss why this observation led to a development in the scientific ideas about the nature of the electron. So pause the video now, then unpause the video when you want to go through your answer. So the first one is just rote knowledge, you've just got to learn it. So an electron volt is the work done when an electron is accelerated through a potential difference of 1 volt. Remember, a potential difference will always cause charged particles to accelerate through them. The next one, you've got to remember that the work done is equal to charge times by potential difference. That's an equation you've just got to remember, and therefore we know EK is equal to a half mv squared. So what we can do is, because we know in this situation that that the work done is going to be transferring kinetic energy into electrical potential energy, we can equate the two equations. So we can say VQ is equal to a half mv squared. Now remember, the big V on the left hand side is potential difference, the small v on the right hand side is kinetic energy. So therefore you sub in your values because you know what the electron charge is, you know what the electron mass is from the equation booklet in the exam. So that gives us our value of 5.93 times 10 to the 5 times by the square root of the potential difference. Now for the next question, you know that the de Broglie wavelength is lambda is equal to h over mv. Remember, v is the velocity. Now you can work out the velocity from the previous equation given, 5.9 times 10 to the 5 times by the square root of the potential difference, where the potential difference is 5,000 volts from the question. So you can put all the numbers in and you get 1.7 times 10 to the minus 11 meters. Now electron diffraction patterns were very important because before this, electrons were only considered as particles. Now we didn't expect the particles to diffract, but diffraction occurs when it's for waves. So this tells us that only waves diffract, so therefore in this instance electrons were behaving like a wave. So it was the first evidence of wave-particle duality. Next question. Figure 1 represents the decay of particle X into particle Y and two other particles. The quark structure of particles Q and X and Y are shown on the diagram. Deduce the name of particle X, state the type of interaction that occurs in this decay, and state the class of particles which W minus belongs to. So pause the video now, then unpause the video when you want to go through your answer. Right, so what is particle X? Well, from its quark structure, it's down, up, down, which is a neutron. Next one, what type of interaction occurs in this decay? Well, it's a W minus, so it tells us it has to be via the weak interaction. You could already know this as well because a quark is changing flavour, which is also a hallmark of the weak interaction, and also that there are leptons present in this interaction as well. Then finally, state the class of particles W minus belongs to. This is a fact, it's an exchange particle or it's a boson, same thing. Now in this situation, show clearly how a charge and barrier number are conserved in this interaction, including references to the quarks in your answer. Name the only stable baryon, and then a muon is an unstable particle. State the names of the particles that are produced when a muon decays. So pause the video now, then unpause the video when you want to go through your answer. Right, so the first thing you've got to do is you've got to work out the charge number before and after and the barrier number before and after. So you should be aware by looking at the back of the book the charge and barrier number of each of those quarks present. So you do 2/3 minus a third minus a third goes to 2/3 minus a third plus 2/3 minus 1 plus 0, because we know what the lepton and charge are going to be for both the antineutrino and the electron. You do the same for the baryon, which is a third plus a third plus a third, which is from the quarks beforehand, goes to a third plus a third plus a third plus 0 plus 0. We know that because the electron and the antineutrino are both not baryons. So therefore it proves that both of them are conserved. Now remember, you've got to break it down to the individual quarks and not just give the baryon and charge of the actual baryon itself. The next one is just a fact you've got to learn, which is the proton is the only stable baryon because it's the smallest mass. Then finally the muon is a lepton, so will decay into an electron because that's a much smaller mass than the muon, but also because you've produced an electron, you'll also produce an antineutrino as well to conserve the lepton number in the actual decay process. Next question. More than 200 subatomic particles have been discovered so far. However, most are not fundamental and are composed of other particles including quarks. It has been shown that a proton can be made to change into a neutron and that protons and neutrons are made of quarks. Name one process in which a proton changes to a neutron. Name the particle interaction involved in this process, and then in this show that the baryon number and lepton number are conserved in this process. So pause the video now, then unpause the video when you want to go through the answer. So the first thing you've got to know is the different types. So the most common two types are electron capture or beta plus decay. Now the particle interaction is got to be the weak in both instances. You know this because a quark is changing flavour. It has to for a proton to turn to a neutron. Then finally for each one you've got to write the proton, the baryon number before and after, and the lepton number before and after. Now again, you've got to remember what your baryon numbers and lepton numbers are for your key particles, such as the electrons, protons, neutrons, etc. Next question. The strange quark was used to explain the existence of particles whose tracks have been seen in experiments since the 1950s. These were unexplained at the time and were referred to as strange particles. One of these particles was later named the K plus kaon. State the quark composition of the K plus kaon. Then our K plus kaon decays into a pi plus particle and a pi zero particle. Explain one property which is conserved and one which is not conserved in this decay. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to look at the situation to work out what a K plus kaon is. Now you then look into the back of the equation book and you're given the quark properties, and you've got to be aware that if it's a meson, that's going to have one quark, one antiquark. Now because it's a K plus, it tells us firstly it must include a strange quark or an anti-strange quark because it's a kaon, and that's the definition of a kaon. It's a meson with either a strange or anti-strange particle, and the two quark and antiquark have to add up to give a charge of plus 1 because it's a K plus, and the only one that does this is the up anti-strange. Now you can work this out from the quark properties given in the back of the book. Now in the next one, what is conserved in any particle decay? You've got charge, you've got baryon number, you've got lepton number, momentum and energy mass. The one thing in this case which isn't conserved is strangeness, because where kaons are concerned, you do not have to conserve the strangeness when it decays by the weak interaction. It can change by plus 1 or it can change by minus 1. Next question. Monochromatic light is shone on the surface of a clean metal plate. The photoelectric effect results in electrons being emitted from the surface. State and explain the effect on the emitted electrons if the frequency of light is increased, the intensity of light is increased, and explain how the photoelectric effect supports the particle model of light and not the wave model of light. So pause the video now, then unpause the video when you want to go through your answer. Right, so in the first one, if the frequency is increased, you'll get a higher kinetic energy of the emitted photoelectrons, because increasing the frequency increases the energy. So we'll have a greater surplus of energy after the work function has been removed, so there's a greater kinetic energy of photoelectrons. If the intensity of light is increased, the number of electrons emitted increases because there are more photons per second, and only one photon can interact with one electron, so therefore more electrons are emitted at once. Now the photoelectric effect explains the particle model of light, because the number of electrons emitted doesn't depend on intensity, which it would do if it was a wave. Okay, the emission of the electron only depends on the frequency, because it's given in a packet called a photon, where E is equal to hf. So we know that one photon releases one electron, so therefore the electrons require a minimum amount of energy to be released to overcome its work function from the nuclei of the metal in which it's attracted to. So we know that our electron energy released is the photon energy given to the electron minus the work function. Now if it was a wave model was true, the intensity of the wave would affect the speed of the electrons emitted, and if they were emitted, and also it would be a delay before the electron was actually emitted, because we need time for the electrons to actually receive the energy. However, in this case, the electron is emitted instantaneously, which tells us it either receives the energy all at once or not at all, which can only occur if the energy is received in the form of a particle, a photon. Next question. The threshold frequency of lithium is 5.5 times 10 to the 14 Hz. Calculate the work function of lithium stated in an appropriate unit. Then calculate the maximum kinetic energy of the emitted electrons when the light of frequency 6.2 times 10 to the 14 Hz is incident on the surface of the lithium sample. So pause the video now, then unpause the video when you want to go through your answer. So work function is equal to h times by the threshold frequency, because E equals hf, and therefore the work function is equal to this energy when the frequency is equal to the threshold. So you would do 6.63 times 10 to the minus 34, the work function, times by 5.5 times 10 to the 14, the threshold frequency. So you get 3.65 times 10 to the minus 19, and the work function is an energy, so the units are joules. Now the maximum kinetic energy is going to be the total photon energy, which is hf, so you do the Planck's constant times by the frequency, which is given in the question, minus the work function, which you've worked out in the previous question, so it's 4.6 times 10 to the minus 20 joules. Next question. The graph shows the results for an experiment to demonstrate the photoelectric effect by illuminating a clean metal sheet with light of increasing frequency. State the quantity and its unit, which could be plotted on the y-axis to produce this graph. Then the threshold frequency is shown on the graph. Explain why there is a threshold frequency. So pause the video now, then unpause the video when you want to go through your answers. So firstly, what is the y-axis? You've got to remember that we've got to measure it from the actual investigation, and the one thing we measure is either the maximum kinetic energy of the emitted photoelectrons, which is measured helpful with the current, or you could also have it as the stopping potential, which is given in the units of V, because it's a voltage. Now the next one, B, what is the threshold frequency? Well, it's the idea that because one photon is absorbed by one electron at a time, and the photon energy is given by E equals hf, therefore there's a minimum amount of energy needed for the emission of the photoelectron, because the electron is attracted to the nucleus of the metal it's part of, which is called the work function. Now the energy which can be given to overcome this work function is only dependent on the frequency of the photon. So that threshold frequency is the minimum frequency which provides the energy of the work function. So that's why we would need a threshold frequency. Next question. The discovery of the Higgs particle was an important contribution to our understanding of particle physics. Describe the standard model for subatomic particles, and you should identify the fundamental particles and the composition of the particles we observe. So pause your video now, then unpause your video when you want to go through your answer. Right, so what are we aware of? So we've got the fundamental ideas of, we've got quarks and we've got leptons. Now baryons are made from 3 quarks and mesons are from 1 quark, 1 antiquark. And you've also got your leptons. Now there are 3 leptons as well. So you've got your electron, your muon and your tau. Now the baryons and mesons are made from quarks, and there's only 6 types or flavors of quark: up, down, top, bottom, charmed and strange. And finally, each particle, whether a quark or a lepton, also has its antiparticle equivalent. So you've got to be well versed in what the particle zoo actually is. Next question. Describe the interaction that is responsible for keeping the protons and neutrons together in a stable nucleus. You should include details of the interactions in your answer, and then the nuclei can decay by alpha decay and by beta decay. In your alpha decay, only 1 particle is emitted, but in beta decay there are 2 particles emitted. Explain how baryon number is conserved in alpha and beta decay. So pause the video now, then unpause the video when you want to go through your answer. So, to answer this question, what you've got to consider is what interactions are holding the protons and neutrons together in the nucleus. So it's the strong interaction, that's just a fact you've got to remember. And the strong interaction acts between hadrons because it only works on quarks. So therefore only baryons and mesons will interact via the strong interaction. And now the strong interaction, as you should be aware, is mediated by the gluon or by the pion. It's called the gluon on the particle level and the pion on the quark level. Now the facts you need to remember of the strong interaction are as follows. It has a very short range because the gluon/pion is such a massive particle, less than 5 femtometers. So you get an attraction up to 5 femtometers. Femtometer being 10 to the minus 10 meters, okay, and then as a result repulsive, less than 1 femtometer, and is 0 beyond 5 femtometers. So which is why you get your nucleus occurring at about 4 to 5 femtometers, whilst you don't get the nucleus ever crushing to a point because it's repulsive, distance is less than 1 femtometer. Now in the second question, you've got to consider what's happening in alpha decay and in beta decay. Now in alpha decay, there's no actual change of the nucleons in the nucleus. All that is happening is 2 protons and 2 neutrons are being removed from the nucleus. So therefore the baryon number and the lepton number are being conserved in this instance because nothing is actually changing type. We've just got things separating from the nucleus. Now in beta decay, a neutron turns to a proton. Now they've both got a baryon number of 1, which indicates that the baryon number remains constant, but they also in beta decay produces a beta minus particle and an antineutrino. Or if you're considering the beta plus decay, you would have the beta plus particle, the positron, and the neutrino produced. Now, but all these particles are leptons, so therefore they have 0 baryon number, indicating baryon number will be conserved. Let's have a look at our next question. Kaons are mesons that can be produced by the strong interaction between pions and protons. The following equation shows the reaction in which a kaon and a lambda particle are produced. Now, the kaon decays by the weak interaction, and you can see an equation shows an example of kaon decay. And then, so state one feature of this decay that shows us an example of the weak interaction. Then finally, there's been considerable advances in our understanding of particle physics over the past 100 years. Explain why it's necessary for many teams of scientists and engineers to collaborate in order for these advances to be made. So pause the video now, then unpause the video when you want to go through the answers. Right, in the first one, you've got to consider what you've got to have on the other three particles to have these ideas. Okay, so if you think about the following, right, you should know that the proton is up, up, down, and that the pi minus is anti, up, down, because they're the only two of quark antiquarks that can add up to give you a baryon number of 0 yet a charge of -1, whilst also having a strangeness of 0, because if there was a strange particle in the pi minus, well, therefore it will become a kaon. Now you can also work out the kaon structure by the same methodology. You need either a strange or anti-strange in there because it's a kaon, and you need a particle antiparticle that'll add up to give a charge of 0 and a baryon number of 0 as well. So what you can work out firstly is that there's a baryon on the left hand side and a meson, so therefore we've got a baryon number of 1, okay, on the left hand side. Now we need a baryon number of 1 on the right hand side, so therefore because the Ka0 is a meson, that tells us the baryon must come from lambda 0, so that must be a baryon, so it's got to have 3 quarks. Secondly, we know that it has a charge which is 0, so we've got to also consider as well that because there's no strangeness before and there's strangeness afterwards, and it's via the strong interaction, strangeness has to be conserved, so therefore we do need a strange quark to counteract the anti-strangeness of the K0. So therefore the only combination of 3 quarks which will add up to give you a charge of 0 and a strangeness of 1 is going to be up, down, strange, which is what our answer is. Now in the next question, we know that strangeness is not conserved because it's via the weak interaction, and strangeness can change by +1 or -1 via the weak interaction. And then finally, this is a general thing, and that's the idea that results have to be independently checked or peer reviewed before they're accepted or confirmed, and it's a lot easier to do that in teams. Particle accelerators are very expensive, and collaboration helps spread the cost of building them. And then also, if you work as a team, you have many skills and disciplines in that team, which is a lot better than just having one set of people there. Let's have a look at our next question. A nucleus of isotope radium decays to produce a beta minus particle, a nucleus of actinium, and a particle X. Identify what X is. State 2 characteristics of X that make it more difficult to detect than the beta minus particle, and explain why the specific charge on the actinium nucleus is greater than the specific charge on the radium nucleus. So pause the video now, then unpause the video when you want to go through your answers. Right. First one, we know that if a beta minus particle is being produced, you've got to have your antineutrino as well to conserve your lepton number. Because if you produce a beta minus particle, you also produce a neutrino, an antineutrino as well. Now, what 2 characters of the antineutrino do you know? That they only work by the weak interactions, they're very weakly ionizing and have weak interactions with matter, they have no charge, and they've got 0 mass as well. Now, why is the specific charge on the actinium nucleus greater than the specific charge on the radium nucleus? Well, actinium has 1 more proton. We know this because beta decays happen, so a neutron is turned to a proton. And then actinium has 1 less neutron because the neutron is turned to a proton. So therefore, when we work out specific charge, which is charge over mass, the charge is increased, but the mass has got smaller. So the mass has got the same for actinium, so therefore it will have a high specific charge. Right, next question. Describe the interaction that's responsible for keeping protons and neutrons together in a stable nucleus, and then nuclei can decay by alpha and beta decay, in the decay where 1 particle is emitted, and beta decay where there are 2 emitted particles. So we've already had a look at this question already. So you've got to remember this idea of your strong interaction, and you've got to remember the idea of alpha and beta decay. Right, so in this revision session, hopefully if we've been successful and we've learned in this revision session, we can answer A-level physics examination style questions. We can assess our understanding on A-level physics, including particles and radiation. And finally, we can understand what topics we need to improve upon for AQA A-Level Physics. So thank you very much for watching this revision session on particles and radiation for AQA A-Level Physics. Thank you very much for watching, and have a lovely day. Hello and welcome to this revision session on electromagnetic radiation, which is the topic in AQA A-Level Physics. So in today's revision session, we're going to focus on answering examination questions on the A-Level Physics topic of electromagnetic radiation. So if we've been successful and we've learnt in today's lesson, we should be able to answer A-Level examination style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for A-Level Physics. So how do we prepare for this revision session? Well, when you're doing this revision session, complete this work on a piece of paper and divide this piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this section write down your working out and answers to the questions in the revision session. Now when you're doing this, make sure you write out your answers in full sentences and show your full working out, whilst on the right hand side write down any piece of information which you find useful or any hints and tips on answering questions from this revision session, and at the end of the revision session write up these notes into a revision sheet for you to use independently. So how should you be revising A-Level Physics? So first step is learn the key facts. So use your revision guides, class workbooks, student prep notes, textbooks to learn the key ideas of the course. Now to learn this knowledge, you may wish to make mind maps or write out the notes yourself. You may want to then after this test yourself by using Caboodle, Seneca, your own knowledge checkers to quickly test your own knowledge, and you may wish to do this retrieval process from your own cue cards. Then the final step is practice and examination questions. So to do this practice, you use exam prep books, homework books, supervised study books, additional workbooks to answer examination questions and mark your own work, and you may wish to download your own past papers to do this. So the steps of learn the key facts, testing yourself and practicing exam style questions are what you should be doing to revise in A-Level Physics. So what are we going to cover in this revision session? Well, we're going to be looking at electromagnetic radiation and quantum theory, which includes the photoelectric effect, collisions of electrons with atoms, energy levels and photon emission, and finally wave-particle duality. So let's have a look at some multiple choice questions for electromagnetic radiation. So some energy levels of a lithium atom are shown below. A free electron with a kinetic energy of 6 times 10 to the minus 19 collides with a stationary lithium atom in its n equals 1 energy level. The lithium atom is excited to the n equals 2 energy level. What is the kinetic energy of the free electron after the collision? So pause the video now, then unpause the video when you want to go through your answer. Well, for this question, the answer is A, because during excitation due to a collision with a free electron, the atom receives the energy equal to the energy level difference, which is from 8.6 times 10 to the minus 19 to 2.9 times 10 to the minus 19, so it's 5.7 times 10 to the minus 19. So if the electron had a kinetic energy of 6 times 10 to the minus 19 and lost 5.7 times 10 to the minus 19, you're left with 0.3 times 10 to the minus 19. The next question says, this graph shows how the maximum kinetic energy of photoelectrons emitted from a metal surface varies with the frequency of instant radiation. Which graph shows the variation of EK max with F for a metal with a greater work function? So pause the video now, then unpause the video when you want to go through your answers. Well, the answer for this one is C, because in the graph of kinetic energy against frequency, we know that the gradient of the line is Planck's constant, so the gradient has to remain the same as the graph given in the question, but the y-intercept is the negative work function. So if we've got a greater work function, we're going to have a more negative y-intercept. So you've got to choose a graph which has the same gradient as the one given in the question, but a more negative y-intercept. So that answer is C. The next question says a particle has a kinetic energy of Ek and a de Broglie wavelength of lambda. So what's the de Broglie wavelength when the particle has a kinetic energy of 4 Ek? So pause the video now, then unpause the video when you want to go through your answer. Right, the answer here is A, because if the kinetic energy is increased by a factor of 4, then the velocity is increased by a factor of 2, because kinetic energy is proportional to velocity squared, so 2 squared equals 4. So if the velocity is increased by a factor of 2, then the de Broglie wavelength has decreased by a factor of 2, because lambda is equal to h over mv. The next question says evidence of the wavelike properties of an electron is what? So pause the video now, then unpause the video when you want to go through your answer. Well, the answer for this one is C, diffraction, because the emission of electrons from when light hits a surface, the photoelectric effect, the movement of electrons in a current, and the annihilation of an electron with a positron is all particle behaviour, whilst diffraction is a wave behaviour. The next question says, this diagram shows the energy levels in an atom drawn to scale. The transition from E4 to E2 caused the emission of a photon of green light. Which transition could cause the emission of a photon of red light? So pause the video now, then unpause the video when you want to go through your answer. Well, the answer for this one is C, because a photon of red light will have a shorter transition than that of green light, because red light contains less energy as it has a greater wavelength and therefore lower frequency, so therefore the transition of energy levels needed to cause this is going to be smaller than that for green. So the only one which is the case which is a smaller transition than E4 to E2 is in fact E3 to E2. The next question says, the graph shows how the maximum kinetic energy of photoelectrons emitted from a metal surface varies with the reciprocal of wavelength lambda of the incident radiation. What is the gradient of this graph? So pause the video now, then unpause the video when you want to go through your answer. Well, the answer for this one is going to be C. Why is the answer going to be C? Well, we know that the gradient of the line is the change in y over the change in x, so therefore it's ek over 1 over lambda, which is ek lambda. Then that's equal to hc, because you know E equals hc over lambda. That's an equation we were given, so therefore we can say hc is E times by lambda, so that's what the gradient is equal to. So the answer is C. The next question says, an atom in the inner coating of a fluorescent tube absorbs a photon of ultraviolet radiation. This causes excitation of the atom from its ground state. A photon of visible light is then emitted. Which energy level diagram represents this process? So pause the video now, then unpause the video when you want to go through your answer. Right, the answer here is going to be D, because excitation only occurs with the absorption of one photon, because that's what's stated in the question. So there can only be one transition upwards to cause this excitation. But the emission of a photon occurs with a smaller transition than the excitation, because it's a visible photon produced, which has less energy than a UV photon, because it's got a longer wavelength, so therefore shorter frequency. So the transition downwards has to be a smaller difference than the transition upwards. So the only possible combination of this is D. The next question says, which row links both the photoelectric effect and electron diffraction to the properties of waves and particles? So pause the video now, then unpause the video when you want to go through your answer. Well, in this answer, the answer is C, because the photoelectric effect is a particle property and diffraction is a wave property. Those are just facts you've got to remember. So let's have a look now at a few longer questions. So the question says here, line emission spectra of hydrogen and antihydrogen have been compared. Explain in terms of energy changes how the line emission spectra are produced. So pause the video now, then unpause the video when you want to go through your answer. So it's important that you can explain how we get emission spectra and absorption spectra, which link into the energy level differences found inside an atom. So what you would say is that all atoms have energy levels which are discrete, so therefore emitted photon energy is going to be discrete values. So you know that emission is going to be produced when electrons are moved from a high energy level to a lower energy level. Remember, absorption is higher is lower to higher, and emission is higher to lower. So therefore we know that the difference between the two energy levels is going to link into the energy of the photon, which then links into the wavelength and frequency of the photon, which is given in your spectra. The next question says, figure 3 shows some energy levels for a hydrogen atom. An excited hydrogen can emit photons of certain discrete frequencies. 3 possible transitions are shown. So these results in photons being emitted in the ultraviolet, visible and infrared spectrums of the electromagnetic spectrum. To which region of the spectrum do the emitted photons belong? So pause the video now, then unpause the video when you want to go through your answer. Well, it's important that you can remember the different comparisons in energy of ultraviolet, visible and infrared. Now, ultraviolet has the shortest wavelength and longest frequency, so therefore has the highest energy, and the infrared has the longest wavelength and shortest frequency, so has the smallest amount of energy. So this tells us the ultraviolet must have the biggest transition, infrared must have the smallest transition, and therefore visible must be in the medium. So we can see that it's C for ultraviolet, B for visible, and A for infrared. The next question says, two ways to excite a hydrogen atom are by a collision with a free electron or the absorption of a photon. Explain why, for a particular transition, the photon must have the exact amount of energy, whereas the free electron only needs a minimum amount of kinetic energy. Then the surface of a sample of cesium is exposed to photons emitted in each of the three transitions as shown. The threshold frequency of cesium is 5.1 times 10 to the 14 Hz. Determine whether any of these transitions will produce photons that will cause electrons to be emitted from the surface of cesium. So pause the video now, then unpause the video and you'll want to go through your answers. Right, so this one you've got to understand that there's two types of excitation. Now the idea is that they can both be caused, it can be caused by either a photon being absorbed by the atom or a free electron colliding with the atom. Now both will cause the electrons to move to higher energy levels. Now because the photon is a particle of energy, all of the energy needs to be absorbed or none of it absorbed at all, because that's what the photon is, because the photon will only interact on a one-to-one interaction. So an electron, because it's a massive particle and not a particle of energy, can transfer some of its energy and keep the remainder of it. So that you've got to know that for photon absorption cause excitation, it's got to be the exact energy level difference, whilst if you've got an electron, as long as it has that amount of energy, and then there could be some in surplus, it can cause that excitation, because it'll continue to move with the lower amount of kinetic energy if it's given some away for excitation. Now for the next question, what you've got to do is you've got to work out what the work function is going to be from cesium based on the threshold frequency and compare it to the transition to see if any of them would cause electrons to be emitted, because the energy of the transition is going to be greater than the work function. Now you don't have to do all three, because you know that C, because it's the biggest difference, is going to have the biggest energy for the photon, because the photon energy is equivalent to the difference between the two energy levels. So that's the most likely one that's going to cause excitation. Emission of the photoelectron. Now, how would you work that through? So you do work function equals Planck's constant times by the threshold frequency, and you work out the value in joules. You can then divide that by 1.6 times 10 to the minus 19 to get your answer in EV, and you see that it's 2.1 EV. You then look to the energy level differences in the atom, and you'll notice that C has a greater energy level difference than 2.1 EV, indicating that the photon produced in the transition of C from 2 to 1 will cause emission in the photoelectric effect. The next question says, photons each with 12.1 eV are incident on the surface of the cesium sample. Calculate the maximum speed of the electrons emitted from cesium. So pause the video now, then unpause the video when you want to go through your answer. Right, for this question, what you're going to have to do is understand that the total energy supplied by the photon, HF, is going to equal the work function plus the maximum kinetic energy. So what we do is we work out what the kinetic energy is by doing the total energy of the photon minus the work function. So we know that the work function is 2.1 eV from the previous question, and we know that the photon energy is 12.1 eV. So we find the difference of that and then multiply by 1.6 times 10 to the minus 19 to convert our EV into joules, because we want to work out a value for velocity in SI units or SI base units. So therefore we want to make sure that we're not using EV, but in fact we're using joules. We can then substitute that value of 1.6 times 10 to the minus 18 joules into the equation of half mv squared. We know the mass of an electron because it's given to us in the equation book. It is going to be 9.11 times 10 to the minus 31. We can rearrange the equation and work out V to be 1.9 times 10 to the 6 meters per second. The next question says, in a discharge tube, a high potential difference is applied to hydrogen gas contained in the tube. This causes hydrogen gas to emit light that can be used to produce the visible line spectrum. The visible line spectrum in figure 8 has been used to predict some of the electron energy levels in a hydrogen atom. The energy levels predicted from the visible line spectrum are those between 0 and minus 3.40 EV in the energy level diagram. So calculate the energy in EV of a photon of light that has the lowest frequency in the visible hydrogen spectrum shown in figure 8, and then identify the state of an electron in the energy level labeled 0. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, the first thing you've got to do is identify where you're going to get the lowest frequency. Well, the lowest frequency is going to be given on your spectrum by the longest wavelength, because the higher the wavelength, the lower the frequency. So we identify that our wavelength we're going to use is 656 nanometers. We can then say E equals hc over lambda. We know h, we know c, we've got to work out what lambda is, and then we're going to work out what E is then. So we work out E to be 3 times 10 to the minus 19 joules. We can then convert that into EV, because we know that we want the answer in EV for this question. So to convert to joules, we divide by 1.6 times 10 to the minus 19 joules to get it into EV, so it's 1.9 EV. Now when an electron is labelled as 0, we know it's out of the potential well that it's in, so therefore the electrons are free, they're no longer bound to the atom. The next question says, identify the state of an electron that is in the energy level labelled minus 13.6 eV and explain why energy levels are negative. So pause the video now, then unpause the video when you want to go through your answer. Well, it's very important that you note that minus 13.6 eV is the value at the lowest point of this particular energy level. So we call those the energy levels closest to the atom. The lowest value is going to be the ground state, the lowest level an electron can occupy. Now, why are energy levels negative? Well, it's important that to become free or to be set away from the atom, the electron is given an energy of 0, because it's no longer bound to the atom. So if we've got to put energy in to get to 0, it must be starting as a negative number, which indicates why all electron energy levels are given as negative values. The next question says, discuss how the discharge tube is made to emit electromagnetic radiation of specific frequencies. In your answer, you should explain why there must be a high potential difference across the tube. Discuss how the energy level diagram in figure 9 predicts the spectrum shown in figure 8, and show how one of the wavelengths of light is related to 2 of the energy levels in the energy level diagram. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you should be doing for these types of questions is answering every single bullet point one by one. So why do you need a high potential difference in the tube? Well, the high potential difference will accelerate electrons, so when they collide with the electrons the atoms in the atoms in the tube will then be excited, so therefore the electrons inside the atoms of the tube are going to go to higher energy levels. So the next point is asking, what's the relationship between the spectrum and the energy level diagram? So what you would say is, because it is an emission diagram, you would say that the electrons in the atom are going to de-excite, and when they de-excite, they will move to lower energy levels, and therefore it will result in a photon of radiation being produced. The energy of this photon is going to be the difference of the two energy levels, and therefore you can link that into the wavelength by saying E, the energy, which is the difference of the two levels, is equal to hc over lambda. And then what you do for the final mark is then work out a value of lambda by looking at your energy level differences, saying working out the value of E in EV, convert that into joules by timesing by 1.6 times 10 to the minus 19, the conversion factor, then say E equals hc over lambda, to say lambda equals hc over E, pop the numbers in, and you should get a value for lambda which is equivalent to one of the values in the energy level spectrum diagram. The next question says, figure 1 shows an arrangement used to investigate the photoelectric effect. A current is measured on the microammeter only when electromagnetic radiation with a frequency greater than a certain value is incident on the photoemissive surface. Explain why the frequency of the electromagnetic radiation must be greater than a certain value. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this type of question? Well, you'd indicate that frequency links to the energy of the photon, which is absorbed, which is going to be absorbed by the metal surface, and the idea is that E is equal to hf. So therefore you'd have to have a minimum energy of a photon required to move a photoelectron, which links into the minimum frequency of that, because the idea would be that you've got to have a work function to overcome to release that electron via the photoelectric effect. So therefore the energy of the photon has to be at least that value, or above. The next question says the investigation is repeated with a different photoemitter surface that has a smaller value of the work function. The source of electromagnetic radiation is unchanged. Describe the effect that this change in the surface has on the value of the stopping potential. So pause the video now, then unpause the video when you want to go through your answer. Well, what you've got to remember is that stopping potential links into the electrical potential energy, which is equivalent to the kinetic energy of the photoelectron. And we then also know that the total energy of the photon is split between the work function and the kinetic energy of the emitted photoelectron. So if the work function is less, that tells us that more of the energy of the photon is going to the kinetic energy of the emitted photoelectron. So therefore, as the kinetic energy is higher for the emitted photoelectron, you will need to have a greater stopping potential to stop that electron from moving and convert that kinetic energy into electrical potential energy. So I hope you've enjoyed this particular revision session on electromagnetic radiation. So hopefully, if you've been successful and learnt in today's lesson, you should be able to answer A-level physics examination style questions, assess your understanding on A-level physics, and understand what topics you need to improve upon for A-level physics. So thank you very much for watching this revision session on electromagnetic radiation. Thank you very much and have a lovely day.